And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, welcome everybody. Welcome here. Welcome to NEAF 2023, the Sunday edition. We have a really, really great program set up for you this afternoon. And starting with our first speaker. She is a planetary scientist, a geologist, professor at Brigham Young University. Also, you may have seen her, some of you. She's a contributing expert for science discovery on how the universe works. Recently, she's been appointed to a team for Dragonfly, which is a quadcopter which will be searching the moons of Saturn. Please welcome to NEAF 2023, Janie Radebaugh. Welcome.
Good morning. How's everyone today? I hope you're doing well. I'm excited to be here and excited to be able to talk to you a little bit about the Dragonfly mission to Titan. It's going to take us a little while to get there. We're going on a journey in order to arrive at this location. So I'm going to go back about 22 years ago. I found myself bumping along in a Land Cruiser down in South America. We were in the Puna, south of the Altiplano, which is another even higher and drier plateau, and learning about volcanic landscapes and eruptions, and just seeing an ever increasingly alien landscape as we were driving along. And we decided, okay, it's getting rougher, let's all pile into the same cars and continue from here. So leave anything behind that you don't need. And I had a first generation digital camera. It was about this big. This is just 22 years ago. Isn't that amazing to think how far we've come? And I thought, this is just so big, I'll just leave it behind. And unfortunately, I didn't have one of my Fuji, disposable cameras with me. So I left my camera behind on the seat and we continued on. And as I continued, I started to notice a landscape even more bizarre and alien as we went forward. And I'm not pointing this in the right direction, maybe forward, just one. And as we kept driving, the landscape got rougher and rougher. Here we go. And the vegetation disappeared. And suddenly I could see lava flows crawling across the landscape. There were big gravel ridges like we're seeing on Mars. And way off in the distance were some tall little towers. You can kind of see them over on the far right. Little tiny rock towers. And we approached those, we got closer and closer, and they are big, huge pillars that are white, just bleached white, and they have tiny little crystals of quartz. And I stood right next to one and just looked at the beauty coming into my eyes and thought, why are these here? This is like Io, this is like Mars, this is like any kind of planetary landscape I've ever imagined. And where's my camera? I had no camera. Please take this picture for me and send it to me. And I never got any. The only picture I ever got back is one I really do treasure a lot, and that's this beautiful one of all of us just exhilarated coming off of this incredible landscape, and just, I'm way over on the right, and we're all just so happy to be there and see what we saw. So on that day, I vowed, I have got to get back here. I know it took me 5 days to get here, driving in a car from, Buenos Aires and then Salta, and I've got to get back here one day. And it took me I guess it's been about 17 years, but I made it and I got back there. And now I go back and I study these incredible landscapes for NASA. Okay, well, why does NASA care about these places? And this is a video. And it's because they are just incredible. They are bleached white landscapes, these rock towers, and there's no vegetation, so that means the desert is dominating here. It is a wind-carved landscape. And Yeah, I don't know if we're able to get a video up. We were experimenting with this. Oh yeah, here we go. So I just feel like I'm on Mars every time I'm there, walking around on these gravels and trying to examine the rock towers. Why are they here? We think they were one solid layer in the past. And next one, I think, is also a video. And we're trying to understand, okay, you can kind of see they're streaked on the sides because the wind has carved them and eroded them. And so how does the wind carve them into individual towers? Why doesn't it just scrape it all off as one solid layer? Instead, it sculpts them into these towers. And notice they're kind of hard. We can walk on them. And next one, I think I ended it a little early, but next slide. Oops. Let's go back. Yeah, next one. I like to feel like I'm in Star Wars when I'm there and dress like it as much as I can. So here I am, I'm Rey, I'm walking around and trying to see these things. And really they're so beautiful and almost ballistic in shape. They're almost the perfect aerodynamic shape that you can make. They look like submarines or like islands in a stream. And really that's the idea, is that wind is flowing around these just like water flows around islands in a stream. And from overhead, you can see that they're arranged into lanes. So here's a lane right here, here's another lane. And in between those lanes are a bunch of big gravel ripples. And again, this is just like Mars, like other planetary landscapes where the wind is in control and it's dominating and it is carving out the landscape. And they make just such beautiful forms. Look at the gravels untouched. And I mean, you just want to walk right between those and walk off into the distance. And then in some regions, the gravels are kind of dominating, and the towers are just barely poking up here and there, like islands, like glaciers poking up, or mountains poking up between glaciers. And we're out there studying them. This is another video. So here you can really tell that ballistic shape, that streamlined shape. We're walking around on them and trying to better understand how they form and what's happening to them over time. And yes, I don't know if this one will play, but we'll play this one actually next. This is a nice one. Okay, here we go. So here we are. We can just walk around on them. We can place wind meters, anemometers on them and study which way the winds are blowing. And you would think, they've got to be blowing from the left. Or the right to the left here. But it turns out that instead, sometimes the winds blow from the side, like here in this video with we got these smoke candles and put them out and watched what's happening. And in some cases, for this video, it is really kicking and is almost all we can take to just be out there and be experiencing it. So here's the PI of the grant, Laura, is sitting up on top of that. She's Laura Kerber at JPL. And she's just lying down, trying not to get the brunt of the wind, but they're blowing from the side, and you can even see that in the shapes here. So the more we can study these on the Earth, the better we can understand what's happening on other planets. When we look at these landscapes, because we just get a snapshot in time, we don't even know which way the wind is blowing most of the time on these other landscapes. Okay, and next one, sorry, I ended it a little early, this is my fault. So we keep on going back there and keep trying to understand what's happening and what we're seeing. And we also bring some other tools with us. This is another video. This is really video heavy early, and then we'll settle in. But so we bring our little handheld drones, and these are really incredible devices. They take care of themselves, and they fly just about anywhere. So here's some drone footage of Laura walking off into the distance. And so we're kind of flying upwind right here in general. Although right now it's really pretty quiet, so we do have times where the wind is not blowing all that much. And you can see all of them have a really kind of even slope on their backs. They have these orange coatings that we think happens because once in a while a little bit of water creeps into there and sits on the surface, but most of the time the wind is dominating, the wind is in control. And so here we are running across the landscape and really happy. I love being here. It's my favorite place. And she's about to step in water. No, it was gravels. But it gets us every time. It just looks like a little pool of water in between these rock towers. And as we continue off into the distance, we can zoom past these features. We can see volcanoes way off in the distance. We see hydrothermal deposits. And I mean, it just is a landscape that I really think has so many planetary connections in so many ways. Okay, well, what are these like? We'll go to the next slide. There we go. Here is a picture of a bunch of these same things on Mars. And as we always find out on other planets, they're bigger. They're bigger than we have on the Earth on Mars, but they are really similar. They're wind-carved, and they came out of volcanic ash, we think. We're starting to lean in that direction because the ones that we see on the Earth are mostly carved out of volcanic ash, sometimes lakebed clays, so that's exciting for Mars as well. And so why do we care about them for Mars? Well, we're going to go to Mars at some point. We'll bring humans there, and we'll try to live and work on Mars. This will happen. This will happen. And so we have these ideas, well, how do we house ourselves? There's no magnetic field to protect us. So we would like to build some houses, and these are examples of 3D printed houses on Mars. These features right here, 3D printed out of the rock. So that's pretty exciting. You can grab rock and then just print them up. Why don't we just build a house out of the wind-carved ridges and towers that we see on Mars? We already have the natural streets in between everything. We have the blocks laid out. So it seems like it would be really simple to do that and kind of exciting. Okay, well, and that helps us with our exploration of Mars. You saw yesterday from Nikki that we're exploring Mars. We're going there with spacecraft, with these incredible rovers. And here's the landing of Perseverance. Look at the clarity of this image. This is an image from Mars, and it's spectacular what we can see from there. And then there's a little bit here from the lander looking up toward the rocket, and then the rocket looking down toward the lander. And then we also brought with us a little tiny helicopter. And this is a kind of a precursor of what we're going to talk about more later on, but you can see a flight of the little tiny helicopter, and you heard from Nikki that we're at the 50th flight of this helicopter. It was supposed to work once, and it worked 50 times, and it's really hard to fly on Mars. The atmosphere is so thin. So that's exciting for us. We've got this helicopter technology, and we can use it elsewhere. Okay, but we also see, it turns out, we see these features on Titan. On Titan. Titan is a moon of Saturn, and yet we have these features. You can see a couple of arrows pointing towards some really straight landforms. And these straight features right here, how in the world could we get those unless it's from tectonics? We think maybe these features here are straight because of tectonics, but these features are straight probably because they're carved by wind. And so we have these wind-carved ridges also on Titan. What does that tell us about the surface of Titan? Maybe this is volcanic ash. Maybe this is a soft clay. Maybe this is something that is soft enough to be carved by wind. It's also being carved by water, as you can see, or not water, liquid, as you can see in the really sort of ridged terrain here. And the liquid there is a very different kind of liquid. We'll talk about that in a minute. This is a strange image. It's a radar image. We're not used to seeing this compared to visible, but the atmosphere of Titan is very thick, and so we have to use a radar to be able to see through. So you get a black and white image of the texture of the surface, where bright is rough and dark is smooth. We'll look at a few more of those. Okay, so Titan, we've gone all the way out to Saturn. We were at Mars, 1.5 times as far away from the sun as the Earth, and now we are at Saturn and Titan 10 times as far away from the sun as the Earth. And Saturn is so beautiful as we've seen it from Cassini. And you can see the sharpness of the shadow of Saturn onto the rings. You can see the sharpness in the division between the rings. And what I like is the contrast between that and the overall softness of the atmosphere of Saturn. I think it's really got such a beautiful soft texture, especially compared with Jupiter. What about Titan? When we flew by with Voyager, and we even noted this from telescopes, Titan is really unique. It's got an atmosphere, first of all. It's a moon, and it has an atmosphere, and that's unusual. And in fact, it's an atmosphere that's really similar to Earth's. It's about 95% nitrogen, just like Earth's. The other 5% is methane. So we have organics and nitrogen in this atmosphere. And that makes it both Earth-like and then interesting in terms of possibility for life. And so a lot of the impetus for Cassini that was there from 1997, from 2004 until 2017 was to look at Titan and look specifically for any more evidence we can find for life. Okay, back to the atmosphere. Here's a whole array of atmospheres on other planets, and you notice that Titan is sitting there at 1.5 bars. We've got a very thin atmosphere at Mars, 1/100th of Earth's, and we've got a very thick atmosphere at Venus, 90 bars, but Titan is Earth-like in its atmospheric pressure. And actually that would make it very easy to explore with humans. So just keep that in mind. You don't need a pressure suit, but you need a very warm winter coat, as my friend Chris McKay likes to say. We've also seen liquids on Titan. This picture was hanging in the West Wing of the White House for a while. This is liquids on another body in the solar system, the only other body besides Earth that we know of that has got liquids on the surface, but this is liquid methane. So all that methane in the atmosphere can be a gas in the atmosphere, and it can rain and flow across the surface as a liquid. And that's really incredible. It fills up lakes and seas, just like this one here. Doesn't this look like Earth? This looks like Earth. It's got dendritic networks of channels emptying into the oceans and lakes and seas of liquid methane. And they look dark here because this is, again, a radar image. And so dark means smooth. Radar signal is hitting something very flat and bouncing off and not returning to the spacecraft. And so it is a really smooth surface. And so it appears dark here, but we think it would probably be clear in color, unless it's filled with some impurities, which most likely it is, just like other water on the Earth. But it would behave a lot like water. It's a little bit more fluid. So we've got rainfall, we've got erosion, and other kinds of things that are exactly like Earth. So maybe because we have all these lakes and seas, we have what we could say is an ocean world at Titan. This is a really special category at NASA, ocean world, because there's an ocean on the surface just like Earth. But when we look at Earth and Titan and we talk about it in that sense, we don't really mean oceans on the surface necessarily. We mean oceans in the interior. And we mean oceans of liquid water. Okay, well, why is liquid water so important? And it's because everywhere we have liquid water on the Earth, we have life. And so this is where we look in the solar system. And we've started to find out there are a lot of these objects that do have liquid water oceans underneath an icy crust. And these are all the bodies at Jupiter, Europa, Ganymede, Callisto, and the objects at Saturn, the moons of Saturn, besides Titan, Enceladus, Mimas, and Iapetus, possibly those large ones, and maybe even some of the tiny moons of Uranus, possibly Triton. And as we look at Pluto, we are pretty sure that there is a liquid water ocean in Pluto. And what would this look like? Well, you have a crust you can see here, 50 or 100 kilometers thick, and then you have a liquid water ocean simply because you've increased the pressure of that ice. And when you increase the pressure on ice, it melts. And then you keep going down until you get to the deep interior. So we've got rocks, we've got water, we've got organic, we've got methane in the atmosphere. So that's a really special combination. In fact, with all that methane in the atmosphere, there's a breakup of that, and by sunlight, a breakup of the methane, a recombination into longer chain organic molecules. And that might also involve the nitrogen. So we've got methane, nitrogen interacting with each other and making, first of all, things like PAHs, heard of this? Polycyclic aromatic hydrocarbons. These can end up being the building blocks for RNA and other things, amino acids. And so all of those materials are being made in the atmosphere of Titan. We've seen some, we've detected some with Cassini, propane and benzene and acetylene detected by a mass spectrometer on board Cassini. So we know they're being made, and then they settle down to the surface. They snow down gently and land on the surface and maybe get incorporated into mountains right here. They fill up the lakes and seas, so there might be kind of a sludge at the bottom of all these lakes and seas, a sludge of organics. So again, that makes Titan such an interesting place to go and think about the possibility for life. Well, do we know any more about it? This is a video detailing the descent of the Huygens probe down onto the surface of Titan. We did know that we should actually look at this surface in more detail, brought along with us a European Space Agency made Huygens probe that descended down onto the surface. So this is a series of images then stitched together into a movie. And you can see it's a very bizarre landscape, isn't it? And in this case, we're looking at basically true color, but just brightened up a lot because the sun is pretty dim here. And you can see bright highlands, you can see darker lowlands. Those look kind of smooth. They look like maybe they were ancient lake beds. And some erosion happening on those lake beds. Now river channels, right? As we continue to descend down, we can see a few river channels from overhead. Now we're going to land on the surface. And look at that. You can see the lamp for a minute illuminating the surface. There are rounded cobbles in this river channel, which means that there's been fluid that's flowed here and broken up these rocks and rounded off the edges, just like you see happening in river channels on Earth. And you'll see a parachute moving by. Look at that. Isn't that amazing? The parachute shadow. And in just a minute, I think we see a dewdrop falling. So that's interesting. We are seeing actual rainfall of some kind. It's not like a deluge right now, but we know that rain is actively falling on the surface of Titan, which is exciting. And then there's also the lamp spot there that's causing distortion of the image. And really just such a spectacular terrain. Okay, oh, there's the dewdrop. And here's the sun in the sky. Okay, and let's go on to the next image. There we go. Okay, so as we can see, descending down, there are these really evolved river channels telling us, again, this is an active landscape. It's not an anciently active fluvial landscape like Mars, but this is forming today and happening today. The wind is blowing, the rain is falling on Titan today. And in fact, it's carving itself into channels. Here are a bunch of river channels right here. You can see showing as bright in radar, which means they're rough. The edges of a really big crater rim. This one is 300 kilometers in diameter. Massive old impact crater. There aren't many impact craters, which tells us that the surface of Titan is quite young. And otherwise, we would be covered in impact craters just like the moon. But instead, it's pretty young. There are just a few. This one is really notable. And recognize, too, that it's very eroded, just like an impact crater on the Earth. So again, this continues to be really Earth-like and kind of a bizarre landscape. When we look at Titan in the infrared from Cassini, some landscapes start to stand out rather than just the atmosphere. So we have big, bright terrains right here that are heavily incised by flowing rivers. And you can see a kind of orange deposit at the equator, everywhere across the equator. And it turns out that that region, we just barely had the right resolution. I wake in the night sometimes thinking, oh, if we'd had twice as bad a resolution, we would never know these exist. But they are fields of sand dunes, hundreds of thousands of sand dunes across the surface of Titan. These are very big. Each of these lines you see here is about 1 kilometer wide and hundreds of kilometers long. Gigantic dunes of sand, 150 meters high. And they're really special features. They interact with obstacles. They tell us which way the wind is blowing, which here, if you had to guess, probably say left to the right. And that's true all the way across Titan. The wind is blowing at the surface from the west to the east. And that's at odds with what's happening in the upper atmosphere, so this really helps us understand what the wind is doing close to the surface. The dunes, I always tell the atmospheric scientists, the dunes don't lie, and so we have to explain them, and we have to say what's going on with the wind there. Okay, well, dunes on Titan, is there quartz sand? Here's some quartz sand from the United Arab Emirates. And this sand has been formed over eons of the formation of a big pluton of granite that's got quartz crystals in it, and then it gets eroded. And the erosion will take away everything else but the quartz and leave the quartz behind. Now we can coat it with an iron oxide coating and get the beautiful red that we see in the sand dunes of the Earth. But the sand on Titan is not quartz. There aren't silicates on the surface. There's just water ice. But then we said there are organics. And it turns out the sand is made of organic materials. What is that like? I keep trying to find an analog. Is it grape nuts? Is it plastic, little bits of plastic sand? Something like that in between. It's got to be pretty hard materials so they can survive the formation of these large sand dunes over time. And ultimately, it came from the atmosphere. But after that, we don't know. Erosion, we don't know. Okay, everybody loves sand dunes, right? You've all been to sand dunes either at the beach or somewhere. They're peaceful, mind-expanding environments to just rest on. And they're covered in beautiful ripples. They have beautiful shapes. This is a video. They're always changing and moving. Look at this poor road. It's not going to last much longer, or the dune will move over the road and it will expose it again on the other side eventually, maybe in a decade. Maybe less than that. Sometimes they move very quickly, a couple meters a year in this location in the Salton Sea. And it's another video. The ripples can move really quickly. You can watch it over the course of just a few minutes to hours if the wind is really kicking. This is in the United Arab Emirates. And what you're seeing in the background is the next dune. And boy, it does not look like a mountain. It's a mountain of sand and a big valley in between with a couple of smaller dunes. This is exactly what we think it would be like to be on the surface of Titan. You have mountains of sand spaced apart from each other. And so we go to these deserts because we don't really have this kind of dune in the Western Hemisphere. So we need to go to Egypt and to Arabia and to Southern Africa and try to understand these dunes and study them. And we're dragging right now a ground-penetrating radar. You just slide it along the surface and it will image the subsurface and show the layers beneath. So you can see right here very cleanly the base of the dune. We can see all these rocks cropping out underneath the dune, so we can kind of tell how big they are, which way the sands are moving over time, and that's really useful. And it's also great for me. I bring my students. They love being out there. They love exploring. They love the challenge of taking those tracks off and getting unstuck whenever we get stuck, and helping plan our routes. Here we are in Australia. There are some very old ones in Australia as well, using the old paper maps and the land cruisers. We've been visiting the Namib Sand Sea in Southwest Africa. Look at this beautiful Landsat image. Everything's a little bit colorized, but there you can see those lines of dunes sitting out there on the, against the coast. Big rivers are cutting through. If we look at a digital elevation model of these dunes, you can see how thick they are. They're really, the sand is just standing up there. And this is just eons of rivers transporting the sand there and it being trapped between the oceans and the mountains. And we can fly over them in airplanes and get a sense of what's going on. One thing that stands out to us is the place between the dunes is drastically different than the dunes. And that's kind of interesting to us. Here there are salt flats and clays. And in some of those places, they tell us about older climates from before. This used to be wet, and now it's not. Now it's dry and dead. In fact, this is called dead vlay. And the clays and the salt flats are very different from the dune sands. We think we need to expect that on Titan. The interdune, the place between the dune will be different from the dune. And we can march up the side of this dune here and get a sense of the subsurface. We really love these data. They're very good. They tell us the sand is moving up and down the long axis of the dune. And that's valuable for us in terms of what's going on Titan, where we can't measure that. Here in the United Arab Emirates, and you can see a fence behind, this is the border fence with Oman. You can see clearly the dune versus the interdune. They're very different. And in this location, the interdune gets wet. So we're in a hyper-arid desert, and the temperatures get to 135 degrees in the summer, and it never rains. But the space between the dunes gets fed by the mountains distant and erupts up underneath the surface and feeds massive oases. And in fact, there are big date palm oases all across this region. And okay, this is great. So then we have water in between the dunes here. And this is really important. It helps the dunes grow large. It anchors them in place and helps them become giant. This is a giant mountain of sand behind the truck. And it creates problems for the roads here. You can see the road and the sand kind of dancing across the road. But one thing we've noticed too is that in some places with all of that water, even though it's hyper-arid and pretty dry, you don't see other vegetation here, but you can see an organization to the mounds in the background. You see these? These are algal mounds. There's bacteria, there's archaea, all kinds of things thriving in this really crazy environment. And so we think that the place between the dunes where there are liquids is really good for life. Okay, and file that away for Titan. So we do just want to think about this, and this is a video of flying a drone, but this is just in Utah, pretty close to where I live. I would go there during the pandemic. I couldn't really go out to these distant locations, but I had something really great nearby. And sure enough, you can see there's more vegetation in between the dunes where the liquids can collect there. Okay, oh, next slide, sorry, I did that. So, okay, so we've got all these ingredients, key ingredients necessary for life. We have organics up in the atmosphere, and we have rainfall, we have surface processes that help bring things into the right locations with each other. Look at this one on the bottom, cryovolcanism. We said there was liquid water in the subsurface beneath an icy crust, maybe 50 kilometers thick. Can we bring that up to the surface and have it interact with the surface? Now we have liquid water, we have organics, and that is perfect for life. Maybe you could picture something, well, and maybe it would come out of something like this, and luckily we got to call this Dune Mons, Mount Dune, on Titan, which is awesome. And it just looks like, what else is it? It's got a big pit in the middle, there are flows coming out of it. What else could it be besides a cryovolcano, a volcano of liquid water? So if you can picture something like this happening, this was an eruption, it's a video from Iceland in 2021. We got to go and view this eruption happening, and it was the experience of our life. This is not slowed down, it's just very big. Hundreds of meters high, these fountains, and they cool off at the top, they feed a massive channel at the bottom, and this would happen every 15 minutes, and we just sat there and just in awe. Okay. Oh, here it is spreading out. I was just hoping, can this come down close to the ground? This is another video where I can see it and I can stand on the surface somewhere safe and watch it. And we got lucky, and it did. It came right down by the hill. And even though this is moving pretty slowly and is covered, actually we would say this is quick in lava speak. This is moving along pretty fast. But it's covered with the crust. I'm doing this with my hand because of the temperature. It's really hard to stand that temperature. And we think the same thing would be true to some degree. If you live on Titan and a volcano of water erupted, that would be very hot for you. So you want to think about things in terms of where you are. And we would be able to see a thermal signature of some kind if there could be a cryovolcano. One last one here, video. This one was taken at night when everything is just really cranking, and I'll just kind of let you watch this video. It stands out much better at night. You see the difference in the contrast in light and color when we can watch these volcanoes at night. It's really important. And for another day, I will come back and we'll talk about Io and how exciting this would be for Jupiter's moon Io with hundreds of active volcanoes all across the surface. And certainly fountains like this erupting now, but bigger and more beautiful. Maybe not more beautiful. Okay, we were talking about dunes though. Let's go back to the dunes. This is a nice painting by Mike Carroll showing a mountain of dune, and we've got a landscape in front of us, maybe gravel ripples. And can't we just go there? So here's another video. Yes, we can go there. Here's the punchline finally. We are going there with Dragonfly. And this is a really exciting mission idea. This is a drone quadcopter. This is what will happen. It will take off, it will just drop out of a shell. It's going direct into the atmosphere, it will drop out of a shell, fire up, and start flying across the landscape. And it will land in this dune-covered landscape, hopefully with some river channels, maybe some interdune deposits that have got some liquids. We don't want too many liquids because we want to be able to take off and land in this environment. We'll stay here, we'll open up a dish, and the dish will communicate direct to Earth. So we need to be near the low latitudes, near the equator, and the seas are up at the poles. We'll do some analyses for a couple of our Earth weeks and then pick up and fly again to the next location. It's really exciting. We've not done space exploration like this before. So it's going to fly, it's going to land, and take off again. We've been selected for flight. We just passed our first review with NASA, so we get to start building at this point. It's very exciting. Okay, I mean, what is this thing like? It's as tall as I am, excuse me, and you can see me holding just one blade, so there are two of these blades across for each of the 4 rotors that you see, and then they're redundant, so 8 total sets, and 16 of those blades all across the body. Why are we going there? It's easy to fly in this environment. We've got an atmosphere like Earth's, as we've been saying. And then also we've only got a gravity like the moon. This is a perfect place to fly. The temperatures are cold, so we shouldn't have really big convective thunderstorms. We should be ready for that in case. But these big quadcopter drones are very stable to fly. If any of you've got your own, you know that they're pretty indestructible. So where will we go? We're going to go to this location right at the equator. You see a circle there for Selk crater. We want to be by a crater, but we also want to be by sand dunes because we know that organics are in the sand dunes. So let's say we land here and we get to go across 6, 10, however many dunes, and then continue to fly up this ejecta blanket, which might be made of water ice. And that's really exciting. Okay, we've got an MMRTG, so we've got a radioactive power source back here that charges up a battery. And as we said before, we go direct into the atmosphere and we come down on parachutes for about an hour and a half because the atmosphere is very thick, and then just start flying around on the surface. We're going to use what's called a leapfrog strategy because remember, it's about an hour and a half communication delay to get from Saturn to the Earth. So you can't operate this in real time. You've got to let it have some autonomy. So what we'll do is we're coming into land this first time right here. We will look at the next place that we want to land and then come back and land. The very first landing will be probably the scariest because we don't really know exactly what to expect. And so we'll land in that first location, but there will be a lot of sensors on board to help in indicating where we should go. And then after, we know where to fly to the next one. And then we continue doing that leapfrog. We fly over a new location, come back to the old one, and travel across the landscape in that manner. We think we'll have about 3 years of exploration, which is really exciting. We'll hopefully go to dozens of locations. We've got the power to do that. But even one single landing, honestly, in my opinion, one landing, one scoop up, as we'll talk about in a minute how we can detect the materials, that to me is worth the entire mission. But we've got a long one ahead of us. We've got materials laid out that we want to study, this alpha, which is the dunes, the beta, which is the interdunes, the space between, and then we've got the gammas and the deltas up on the crater. All those material types that we want to understand and study better. Okay, what about the instruments? So we have a drill on board that will pull materials up, and here's a little video. We'll pull materials up into the belly, which has got a mass spectrometer. So here's the drill working, and this is out of Honeybee Robotics, which is in Pasadena. They actually used to be here in upstate New York, and then they've moved their headquarters, at least, to Pasadena. And they'll drill, pull the materials in, and we'll dump it into the mass spectrometer. We've got a whole array of tubes that we can put these into, and then cause a desorption with the laser, and we can figure out what these molecules are made of to very high atomic numbers. So we'll be able to get a good sense of exactly what the composition is inside of in the materials in Titan. Okay, oh, here we go. The other thing we think is really exciting is this idea of chirality or handedness. Do you see how there's a mirror image of those two molecules? So the mirror image idea is, you know, if you look at life on the Earth, just about 70, it's more than that, I think it's more like 90% of all life has got a right-handed chirality. And this means that life prefers to use that right-handedness. What if we go there and we find, oh, it's just 50-50 chirality? That's a good indicator that maybe it's just organic processes going on. What if we find a left-handed chirality or a right-handed chirality? Left-handed would say, well, there's life there, and it's definitely different from Earth. It evolved differently from Earth. At the distance that Titan is from the Earth, it would have to anyway, because it's very hard to get something from Earth through Jupiter's gravity well all the way out to Saturn. So we still think it would be an individual origin. So we have these other tests we can do to see if there is actual life there. But mainly we'll also be looking at the chemistry of the surface. What kinds of prebiotic chemistry have gone on. We've got a gamma ray and neutron spectrometer. We can look at the surface and the near subsurface remotely and be able to see what's going on there. We've got a meteorology package that can look into the atmosphere. We've got basic things like pitot tubes and barometers and other things that we use for flight on the Earth that we'll have with us. And then we'll also have an ability, basically a geophone from the Japanese Space Agency to listen for Titan quakes. And that's really, really cool. So we'll be able to get a profile of the subsurface and maybe get a sense of how thick that ice shell is. I'm most excited about the cameras. The cameras will look down and they'll see the dunes, they'll see the ripples on the dunes. I'm showing you all pictures of Mars that I get so jealous of every time I see. And even down to the sand, we have sands of Mars that we've been able to see. And I just want a handful of sand because of everything that sand tells you about the environment around. It tells you where it came from and what it's made of. And here's my little collection of sand in my office that you can come by and see when you come visit. Okay, so we're asking these questions. What makes a planet or moon habitable? What chemical process has led to the development of life, and has life developed elsewhere in the solar system? So I'll finish with this. I was trying to make this image of Titan this morning, but I really need my space artist friends to do this for me. I at least colored it a little bit more orange than it would be normally, but didn't get it quite dark enough. And then also we have all the astronauts there on the surface, and again, they don't have spacesuits. They're doing great. They do need oxygen masks though. But we're walking across the surface of Titan, and there are landscapes that could look very much like this one. And I'm looking forward to the ones that might have some of those liquids, those liquid methanes sitting, liquid methane and ethane sitting there in the interdune and maybe interacting with the organics and creating a nice soup for life there. Okay, well, so meanwhile, we're sitting here on the Earth and exploring a little bit. And next slide. And just maybe, or not next slide, this is a video. Just maybe we will see something like this as we're exploring. There will be ripples in between. Maybe picture those mountains in the distance being dunes. And we would go at about this pace across the landscape, flying in our Dragonfly helicopter and exploring the surface of Titan. And this will happen for us. It's coming. Everybody get ready, and get ready to explore a new body. And actually, next one. So, oh yeah, that one. So, oh, I didn't put when we're getting there, unless you saw that earlier. We launch around 2027. It's probably about 2028, and arrive about 2034. And so it takes a long time to get out there, but still, it's happening, it's coming. We're really excited. Thank you. I think I've got time for some questions. Yes?
You know, you have to use spectroscopy to determine what that grow is and things like that.
So this was a question about chirality. I'm probably bumping up at my limit. I know it's done by the mass spectrometer in some way, and so the mass spectrometer is able to detect that chirality. We've got a laser desorption and a gas chromatography mass spectrometer, and something among those will be able to distinguish between that handedness. No, there's no X-ray fluorescence that's going to happen as far as I know on this mission. So thank you. Yes?
Were there any collaborations or lessons learned between Ingenuity on Mars and your team?
The question is, are there lessons learned from Ingenuity? And what's interesting is that Dragonfly was selected and started to be designed and gotten ready kind of alongside Ingenuity. Both were sort of happening at the same time, but not really communicating a lot with each other. But I am certain that we'll be talking to each other and thinking about what kinds of things we learned from Ingenuity. It's amazing that they got to be these pioneers and do the first flight. The blades are, I mean, just gigantic on this tiny little spacecraft because the atmosphere is so thin. And I think they're at 2,500 RPMs. So just really challenging engineering to be able to get the helicopters to fly. But you might also be aware of the fact, and probably heard yesterday from Nikki, that they'll be using helicopters possibly on Mars sample return. So this worked so well that it's great. It's a new way for us to get around on planetary surfaces. It's really amazing. Something back here? Yes.
Like Titan has a lot of material available for life to thrive. One question I've got is, what kind of life always needs energy? What kind of energy sources are available on Titan?
Exactly, yeah. What kind of energy sources? There have been a couple of ideas. I mean, there is sunlight. There's not a lot, but there is. This is why the cryovolcanic scenario is really attractive, because you have some energy from the water being warm and the volcano having erupted. The other thing that could possibly be used is hydrogen. So it turns out that some life likes to eat hydrogen, and maybe we can see some evidence of that. In fact, I think Chris McKay, who's at NASA Ames, decided to try to look for that. Is there a depletion in hydrogen that we could see from Huygens? And there are some hints of that. That would indicate, oh, the hydrogen's being used by something. And so I think as we look at, for example, seafloor smokers and hydrothermal vents, that's one means of getting it the energy that life needs in the really primitive life. So it could end up being, I feel like it'll be things that we haven't thought of, right? We'll see it and we'll say, how does it can't exist, but it does exist, so we'll have to explain that. And that will be true for wherever it is we find it, Europa or Enceladus or clouds of Venus or the surface of Mars or an exoplanet, wherever it is that we end up finding it. And, do we say it that certainly, that we end up finding it? Probably, right? I think it'll be hard for us to explain. Yes?
We've been bouncing lots of light potential throughout the solar system. So, with all your knowledge of the knowledge of missions that have gone before Dragonfly and so forth, if you were betting on one body in the solar system, whether it's Enceladus or whether it's Titan, or which one do you think is going to give us the evidence that it might exist outside?
So I was asked to place a bet on which body has got the life in the solar system. Well, I've got to say Titan, right? I mean, but Titan has everything, and it's right there on the surface. It's easy for us to get to and to explain. What if it is on Europa, but it's at the seafloor, and it's at 100 kilometers deep? What are the pressures like there? Will we ever get there and get to those seafloor smokers and see it? We'd have to be able to see it way up high. That wasn't your question. Where are we going to find it? So I guess my two favorite will be Titan, and then I like this idea of finding it at one bar in Venus's atmosphere, because we've just not been looking there, and that would serve us right, So, what if we had oceans on Venus in the past? Maybe we could even transfer some things back and forth between Earth and Venus, and then as the oceans evaporated under the heat and the pressure, there's a little oasis found at one bar in the clouds, a cloud city. And I just think it's a fun idea. Maybe most likely too is Mars, because it's so close to Earth. It would have to be buried under the surface, I believe. Yeah, and with it's been bombarded, there's no protection. It had to have hidden itself away somewhere. Way up here. No, we wish we could have an orbiter, but we had to fit into the New Frontiers cost cap, and this is about $1 billion mission without the rocket. And so without a flagship, we just wouldn't be able to do that and have an orbiter and be able to fit under the cost cap. Communicate direct to Earth with a little antenna that folds up, built at Lockheed. Yep. Exciting, yeah.
Is there a theory how Titan was formed?
We think that Titan formed around Saturn in essentially like a mini nebula. The same thing probably happened at Jupiter. So as the large objects were forming in the solar system, they started to collect lots of objects around them, and smaller ones that formed started to be attracted to those larger ones, and also probably just formed in a nice temperature gradient away from those bodies. That's really clear at Jupiter, where we have Io that's got no liquid water. Europa's got 10% water. Ganymede and Callisto have 50%. So you see a nice thermal gradient that could have existed at Jupiter. Saturn's story is a little more complex because the moons are kind of different from each other in some ways, and they don't seem to have a regular size progression like we might potentially expect. Titan is quite big, but it's a little ways away from Saturn, I think 20 Saturn radii. So there's another idea out there, and then we have to explain the rings of Saturn. Have they been alive for the whole solar system, or are they transient? For a while, it was thought they were about as old as the dinosaurs, 100 million years old. So could you instead maybe disrupt this Saturn system more recently and bring a lot of objects in? Again, that's a catastrophic explanation, and most of the time we like to sit with the more kind of easy to understand, simpler explanation. But at the very least, where it formed, which is at this distance, it could get a lot of the carbon it needed and the nitrogen it needed to build that methane and then the nitrogen atmosphere. Yes?
A question about cryovolcanism. So I think
the surface of Titan is moving pretty rapidly, like within two years, two different observations showed surface features moving like dozens of kilometers. And I'm wondering how that compares, like this rotation of the outer shell of the subsurface ocean, how that compares with other bodies, and also how that affects the ability to have like sustained volcanic activity, like if you have like a hot spot to make a shield volcano, but it's rotating quickly, and how that affects cryovolcanism.
Great questions. So what you're referring to is this idea that we have observed some landforms. I'll note that we haven't really precisely located our maps on Titan's surface yet. This is a NASA data issue. Data is a really important thing to work with and really important to get secured and to use correctly. So there are groups have been lobbying, can I make a controlled map of Titan? And that's not come yet. So when and where do we get the money to do those kinds of things? Then we know exactly where things should be located compared to how they were observed from the spacecraft. So even despite that, we can say it looks like some things have moved by maybe a couple dozen, I can't actually remember if it's meters or it must be kilometers, a couple dozen kilometers like you said.
I remember hearing like
Yeah.
20 or 30.
Okay, so that might be right. So how would that happen? It's just because if you have a liquid water ocean, that's decoupled the crust from the interior. So things can kind of shift around and move really quickly on this ice shell compared to where we think it should be, right? So if that happens, then this is a good question. How does that affect the magma pathways? Do they come directly from the ocean? That's a lot of lithosphere to come through. So we think it probably has to get forced up and make magma chambers of liquid water first and then erupt later. And on Earth, those silicate magma chambers are long-lived. They can be there for tens of millions of years, and they can feed those volcanoes from up in the crust. Can that same thing happen with water? There's a density problem and a buoyancy problem. Water's not buoyant. It likes to sit down in that ocean. So something needs to force it up. So I think there are a lot of unanswered questions about this cryovolcanism because we haven't seen a lot of it. And also, we think the best places at Titan's surface for cryovolcanoes is at the poles. And so then you'd have a little bit less shifting going on and less disruption of that. Great questions. A couple more? Way back there. Oh, sorry. I'll come back to you. Yeah. One more time. What did we learn from Cassini to help us with Dragonfly? We learned a lot of really important lessons about Titan. I mean, again, this idea that we wouldn't have known there were sand dunes on Titan. In fact, my friend Ralph Lorenz has written a whole lot of papers about Titan. And in one of his papers, he decided to just cover it and just say, there could be dunes on Titan, but I'm sure there aren't. And so then he got to write the follow-up paper, Dunes on Titan, you know? So this is what happens. We've got to go there and just look and see. And in fact, I think we expected the whole surface to be covered in seas of methane because it's saturated in the atmosphere. That's what we could see from telescopes. But it's not seas covering the whole landscape. They're only about 2% of Titan's surface is covered in these lakes and seas. So that was another surprise. And instead, it's just got a really heavily eroded landscape like Earth. So I think we learned, oh, this is a place that we can recognize, somewhere that we know and we understand with a great, perfect atmosphere for flying. So let's go back and study it more. The thing we really don't know about for Titan, I feel like still, is materials. What is everything made of? What are these organics? How do they form? What is their texture, their hardness? And I don't think we'll make much progress on that until we get there and pick it up.
The heat source, give it energy. Would that be an experiment that could actually promote growth of life?
Ooh, that's a really good question. So I kind of think the easier thing might be, well, easier or we worry a little about planetary protection, and that's both protecting Titan from us, and then if we were to return something, protecting the Earth from Titan, right? We don't know how those things play well together. You heard about that yesterday from Holly. So what we could do instead is know what those materials are. Now we can do lab experiments. And I bet we'll do those for sure. Like, okay, we've got these things. Can we make life happen? And what does that require? That's an exciting idea. Yes?
Will Dragonfly be a lot more advanced
Yeah, the atmosphere won't matter too much. We'll transmit in the radio, and so it should go right through the atmosphere. But we should be able to get the pictures back in about an hour and a half. And then same thing, communication, sending a signal. So this is an interesting thing. You know, we're all sitting in a control room, and okay, we send a signal, and now we all kind of wait for an hour and a half, go get something to eat, come back, you know. So, I mean, really, it's a lot of time to wait. Well, I guess that's 3 hours because it's round trip. So that's a whole, I mean, it's just, these are so far away. It's incredible to me that we're so far away, and we're still able to see this world that's like the Earth and be able to go there and explore it. It's exciting. Last question.
Does Titan have any weather that can be dangerous to the mission? Too high, tip it over?
We've got to worry a little about weather. It turns out that the temperature all across Titan is 90, I think it's 91 degrees. And it doesn't matter if you're at the poles or the equator, and it's because the atmosphere is so thick and dense. So because you don't have big temperature differences, that keeps everything pretty calm. We have seen some clouds build. In fact, I pulled up a JWST picture and I didn't put it in. So go look at this, look up JWST Titan, and you will find a picture, and it's compared with a Keck image taken a couple nights later, and the cloud has moved significantly across the surface. So that's at least the upper atmosphere. We'll be down low near the surface, and we really plan for things to be pretty calm and easy. And but we'll find out. I don't know. I think it's exciting. Of course, it's not exciting to think about, oh, we could get blown over. We just don't think that'll happen because it's so big and so heavy and dense. I just am very excited for this mission, and I think it'll be great to see what it will tell us. I've appreciated being here. Thank you so much.
Thank you very much, Janie. That was wonderful. Thank you. Thank you. One moment, folks. I have to give you an update. The 1:30 showing, Felix showing, is unable to get here. He's in Texas waiting the launch of SpaceX's Starship. In his place, we have Kevin Schindler from the Lowell Observatory to come in and give us a talk on the Tombaugh telescope that they've been able to reacquire. It's actually a fascinating story behind it, but Kevin will be here to fill in the place. We apologize, but it's not going to be available today for Felix. Thank you.
Welcome to ZWO, the astronomical equipment brand that has been making astrophotography easy and fun for over a decade. Our founder, Sam Webb, established ZWO in 2011 with a mission to challenge traditional thinking and build an intelligent astrophotography ecosystem. Over the years, we have taken innovation and ingenuity as the key to our business growth, and years of dedication has made us a leading brand in the astrophotography market. Multiple of our camera models won the Hot Sky Product Award by the Sky and Telescope magazine in 2016 and 2017. In 2018, we released the game-changer ASI Air, a smart controller device that revolutionizes the way astrophotographers capture and process images of the night sky. In 2021, ZWO released the Harmonic Mount AM5, another addition to ZWO's ecosystem of astrophotography equipment. Every year, ZWO introduces more than 10 new products and brings new technology to the astrophotography field. With over 40 patents, including 2 pioneering invention patents, our company has been recognized with several prestigious titles by the state government that acknowledge our commitment to innovation and technological advancement. We also take great pride in our commitment to quality control, and every aspect of the production process, from the initial design to material selection, testing, assembly, certification, and beyond, is subject to rigorous and meticulous control measures. This level of attention to detail is what sets us apart from the competition. At ZWO, we understand that creating outstanding hardware products is just one piece of the puzzle when it comes to providing a streamlined astrophotography experience. That's why we are equally committed to developing cutting-edge software products that work seamlessly alongside our hardware offerings. The ASI Studio is an all-in-one astrophotography software platform that is specifically tailored to work in tandem with ZWO cameras and provides a range of functionalities, including planetary imaging, video stacking, DSO imaging, live stacking, simple post-processing, bits files preview, and more. The ASI Air mobile application is tailored to the specific needs of astrophotographers, providing an integrated workflow including camera control, mount control, EAF control, precise focusing, auto run, post-processing, and many other functions. With our ASI Mount mobile application, users can effortlessly take control of their mount using mobile devices, eliminating the need for hand controllers or being tethered to the mount. It is the shared love for astrophotography that unites us all and drives the ZWO team to continue pushing the boundaries of what's possible. Together, we have traveled across the country in pursuit of the perfect shot of the night sky, leaving footprints from the picturesque landscapes of Dali and Guilin to the rugged terrain of Daosheng, Dunhuang, Inner Mongolia, and Xizang. We believe that by immersing ourselves in the natural beauty of our surroundings, we can gain a deeper appreciation and understanding of the universe we seek to capture. Moving forward, ZWO remains committed to its mission of making astrophotography easy and fun for amateur astronomers worldwide. Our goal is to enable enthusiasts of all levels to explore the wonders of the universe with ease and precision, so they can focus on what matters most, discovering the beauty and mysteries of the cosmos. To empower and inspire everyone's journey in astrophotography.
We're very pleased to announce our new StarSense Explorer Dobsonians. The telescope tube features a larger aperture than the other StarSense Explorer telescopes. It also has a 2-inch Crayford focuser that accepts both 2-inch and 1.25" format eyepieces, and also has a custom pointing knob to help you precisely aim the telescope at your target. Both the tube and base have carry handles at their balance points, and of course, the exciting StarSense Explorer dock. Simply place your smartphone in the dock and launch the app. Choose from the best objects to view, then just move the telescope to follow the arrows to your target. When it's ready to view, the bullseye turns green. It's easy to do because of the patented StarSense technology.
If you were asked to visualize a typical astrophotography rig, what would it look like? This was how things have looked since the launch of ASI Air in 2018. And this is how it looks now. Thanks to the continuous innovation and new technology ZWO brings to the market, with the latest additions to its lineup, this rig is packed with all the gear you'll need to capture breathtaking images of the cosmos. Introducing the ASI 2600 MC Duo that seamlessly integrates the imaging sensor and guiding sensor into one powerful device, needing only one cable, which reduces potential cabling issues and greatly improves setup speeds so you can spend less time on preparation and more time on capturing the beautiful universe. The 1/1.8-inch guide sensor taken from the ASI 220mm mini camera combined with the IMX571 from the ASI 2600 MC provides stunning performance even when guiding using a 7nm duo-band filter in good sky conditions. A rotary knob controls guide sensor focusing, designed to simplify the process of making two sensors both in focus in one optical system. This combination of guide and imaging sensor in one camera creates an imaging solution that ensures both sensors parfocal over long periods of time, which reduces complexities by removing the need for a separate guide camera and off-axis guider. Duo does it all. And this is the all-new ZWO Astrograph from the FF Apochromatic Refractor series. This series features a flat-field Petzval quadruplet design with two ED glass elements, offering excellent control of chromatic aberration. The ZWO FF series APO refractors create beautiful-looking stars. RMS radius at the center of the field of view can be as small as 2 nanometers, perfect for both visual use and astrophotography use. Differently from normal refractors, the self-flattening design of ZWO FF series does not require a specific back focus from the rear lens, providing freedom to use any filter wheel, any off-axis guider or accessory without the worry of calculating the correct distance from the flattener. ZWO's matching reducers widen the field of view, offering a new perspective from your telescope, and with reduced image capture time. Still, 55mm back focus distance must be maintained when using our reducers. The rigid dual-speed focuser comes with a new type 360-degree rotator with scales and a finder base, making focusing easy and quick. Matching with ZWO EAF, the electronic automatic focuser, it will bring an incredible using experience. The new ASI Air Plus 256G offers an increased eMMC storage space and improved performance from the ZWO custom compute board. With short exposure, the total imaging efficiency will be improved by about 26% compared to its predecessor. The FPS on video mode also improves by about 30%. And finally, we are proud to introduce our new AM3 mount. The new high-performance harmonic mount offers astrophotographers exceptional performance at an even more affordable price. It carries a payload of up to 8 kilograms with no counterweight, and up to 13 kilograms with the addition of a 5-kilogram counterweight. The newly added Bluetooth unit makes wireless connection without hand controllers possible. Carry less. Capture more. Enjoy yourself under the starry night sky. To empower and inspire everyone's journey in astrophotography. Welcome to ZWO, the astronomical equipment brand that has been making astrophotography easy and fun for over a decade. Our founder, Sam Webb, established ZWO in 2011 with a mission to challenge traditional thinking and build an intelligent astrophotography ecosystem. Over the years, we have taken innovation and ingenuity as the key to our business growth, and years of dedication has made us a leading brand in the astrophotography market. Multiple of our camera models won the Hot Sky Product Award by the Sky and Telescope magazine in 2016 and 2017. In 2018, we released the game-changer ASI Air, a smart controller device that revolutionizes the way astrophotographers capture and process images of the night sky. In 2021, ZWO released the Harmonic Mount AM5, another addition to ZWO's ecosystem of astrophotography equipment. Every year, ZWO introduces more than 10 new products and brings new technology to the astrophotography field. With over 40 patents, including 2 pioneering invention patents, our company has been recognized with several prestigious titles by the state government that acknowledge our commitment to innovation and technological advancement. We also take great pride in our commitment to quality control and every aspect of the production process, from the initial design to material selection, testing, assembly, certification, and beyond, is subject to rigorous and meticulous control measures. This level of attention to detail is what sets us apart from the competition. At ZWO, we understand that creating outstanding hardware products is just one piece of the puzzle when it comes to providing a streamlined astrophotography experience. That's why we are equally committed to developing cutting-edge software products that work seamlessly alongside our hardware offerings. The ASI Studio is an all-in-one astrophotography software platform that is specifically tailored to work in tandem with ZWO cameras and provides a range of functionalities, including planetary imaging, video stacking, DSO imaging, live stacking, simple post-processing, bits files preview, and more. The ASI Air mobile application is tailored to the specific needs of astrophotographers, providing an integrated workflow including camera control, mount control, EAF control, precise focusing, auto run, post-processing, and many other functions. With our ASI Mount mobile application, users can effortlessly take control of their mount using mobile devices, eliminating the need for hand controllers or being tethered to the mount. It is the shared love for astrophotography that unites us all and drives the ZWO team to continue pushing the boundaries of what's possible. Together, we have traveled across the country in pursuit of the perfect shot of the night sky, leaving footprints from the picturesque landscapes of Dali and Guilin to the rugged terrain of Daosheng, Dunhuang, Inner Mongolia, and Xizang. We believe that by immersing ourselves in the natural beauty of our surroundings, we can gain a deeper appreciation and understanding of the universe we seek to capture. Moving forward, ZWO remains committed to its mission of making astrophotography easy and fun for amateur astronomers worldwide. Our goal is to enable enthusiasts of all levels to explore the wonders of the universe with ease and precision, so they can focus on what matters most: discovering the beauty and mysteries of the cosmos. To empower and inspire everyone's journey in astrophotography.
We're very pleased to announce our new StarSense Explorer Dobsonians. The telescope tube features a larger aperture than the other StarSense Explorer telescopes. It also has a 2-inch Crayford focuser that accepts both 2-inch and 1.25" format eyepieces, and also has a custom pointing knob to help you precisely aim the telescope at your target. Both the tube and base have carry handles at their balance points, and of course, the exciting StarSense Explorer dock. Simply place your smartphone in the dock and launch the app. Choose from the best objects to view, then just move the telescope to follow the arrows to your target. When it's ready to view, the bullseye turns green. It's easy to do because of the patented StarSense technology.
If you were asked to visualize a typical astrophotography rig, what would it look like? This was how things have looked since the launch of ASI Air in 2018. And this is how it looks now. Thanks to the continuous innovation and new technology ZWO brings to the market, with the latest additions to its lineup, this rig is packed with all the gear you'll need to capture breathtaking images of the cosmos. Introducing the ASI 2600 MC Duo, that seamlessly integrates the imaging sensor and guiding sensor into one powerful device, needing only one cable, which reduces potential cabling issues and greatly improves setup speeds so you can spend less time on preparation and more time on capturing the beautiful universe. The 1/1.8-inch guide sensor taken from the ASI 220mm mini camera combined with the IMX571 from the ASI 2600 MC provides stunning performance even when guiding using a 7nm duo-band filter in good sky conditions. A rotary knob controls guide sensor focusing, designed to
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, thank you, everybody. Thank you. As I mentioned earlier, our next speaker is in Texas, unable to get here, so we have a really, really good speaker to fill in his slot. From the Lowell Observatory in New Mexico, we have the historian there who is going to talk about this incredible telescope from Clyde Tombaugh that was used to discover, at the time, the 9th planet of our solar system. Please give a warm welcome to NEAF, Kevin Schindler. Thank you, Kevin. Thank you.
Thanks, Vince. We're going to have to do a little geography with Vince because Lowell Observatory is in Arizona, not New Mexico, but close enough. So if you get out there, there's so many great skies out there and a lot of good astronomy things to do. Great to be here, and I think we're all very excited to be in person at NEAF after being away for a couple of years. My name is Kevin Schindler again, and I'm the historian at Lowell Observatory in Flagstaff, Arizona. And I've worked there 28 years now. And one of the things I really like about the place is the heritage. Going back to our founder, Percival Lowell, there's so many great stories about him, going through the years to Clyde Tombaugh and on to current science. Lowell is more active than ever. But it's been great to be able to get to know a lot of the scientists or their families. And one of my favorite people to talk about is Clyde Tombaugh, because he was such an inspiring character, a self-taught, self-inspired person, and he achieved so much. And I'm wondering, in this audience, how many people met Clyde at some point? I know there's several in here that have. And everybody that I know that has met Clyde has a great story, usually starting with one of his really bad puns. But he was such an interesting character. He came to a lot of these kind of talks. And so I feel like it's a privilege for me to do honor to him. What I wanted to talk about today is one particular telescope, and I suspect many of you are familiar with this. It's a 9-inch telescope that he built at home. And I call it remarkable for several reasons, because of how he built it. And then also what he used it for, because it led directly to him getting a job at a professional observatory, Lowell Observatory, and that resulted in him discovering Pluto. Without building this telescope, without using it, it's hard to say if he would have been hired. And then when would Pluto have been discovered? That's hard to say. It could have been decades. And then this telescope just came home, as it were, to Lowell Observatory, although it never had been there before. It came home in a kind of an unusual sequence of events. So that's what I want to talk about today. Clyde Tombaugh in this amazing telescope. So most of you, I suspect, know at least a little bit about Clyde Tombaugh, or probably a lot. And so I want to give a little background about who he was to kind of set the stage. He was born in Streator, Illinois. And when he was young, his family moved to Burdett. They were farmers. And so on the farm, young Clyde, during the day, he's working on the farm all day. What do you do at night? In the middle of a cornfield or wheat fields in Kansas. Well, he really fell in love with the night sky. And like so many of us growing up, he was at an age where he was so inquisitive. And then he had a mentor, an uncle, who had a telescope. And he said, Clyde, why don't you take this outside and learn how to use this telescope? And Clyde just fell in love with the night sky. And this is the night sky from his house in Burdett. I visited the home site 2 years ago. And I'm sad to say that I think the house is now gone, because the owners were looking into tearing it down and making it into more farm field, because the house is actually very dilapidated. It hasn't been lived in for years. But I visited the site, and you can see this is what Clyde had at nighttime. Sunset is arriving, and you can imagine him going outside and setting up this telescope that his uncle loaned him. So Clyde got really interested, so interested he decided he wanted to build his own telescope. And he did this. And he read how to do it. He got a magazine, read how to do it, and it was really lousy. And he was disappointed, but he learned. A lot of us, the first time we do something, it doesn't turn out so well, so you keep trying and learning. And so he learned one of the problems he had was when he ground the mirror, he tested it to see how good the finish was in the kitchen. And he read that that's not a very good place to do it, because the changes in temperatures, he needed a place that had very stable air, very still air. And so he talked to his dad and convinced him that, we live in Tornado Alley. We should have a storm cellar. And by the way, this would be a great place to test my mirror for the telescope. So Clyde raised some money himself to buy the cement. And he dug the hole himself with the help of his dad and brothers. And then they got some neighbors that came over to help assemble this cellar. And this is a picture of the cellar that I took a couple of years ago. You can see the end of it to the left, the house is to the right. The cellar is mostly underground. And this proved to be a big difference maker for him in building a telescope, because he could go underground and really do the knife edge test and really tell how good it was. So he built a 7-inch telescope, tested it, and it was remarkable. He was really happy with it. And he built this telescope to give to his uncle. But he did use it some. And he used it to make some planetary drawings. These are some drawings he made with that telescope that he did in color. And so, if he was in love with astronomy before, he was downright passionate about it now, because there's nothing like building your own telescope, grinding your own mirror, and using it to look at the sky and getting really great views. And so he did this, and then he passed the telescope on to his uncle. And of course, he wants his own telescope that he's built himself. So now he starts another project, and he's going to build a 9-inch telescope. And, I'm talking about this like it's really easy for him. He wants to build a 9-inch telescope, so he just goes out and does it. But there's kind of a challenge that he had, and that was financial, because they were growing up on the farm, very tight on funds. It was subsistence farming. The family didn't have a lot of money. In fact, they couldn't afford for him to go to school. That's why he was at home. He graduated from high school and still living at home. And so there wasn't money, but Clyde didn't let that get in his way. He was ingenious. And so instead of, ordering parts or buying parts, he looked around the farm, and he was able to build this telescope, this 9-inch telescope. So he ground the mirror himself, but the other parts he got from the farm. And I'll show you some of this. Many of you have seen this picture. It's kind of a classic picture of him. On the side, the telescope says a Newtonian telescope. And he was really happy with it. This was going to be his telescope, the first one that he made for himself that was really good. So why is this telescope so unique? The first thing is because of how it was made. I told you he used farm parts. And here's a diagram. You can kind of see, you don't need to worry about the lettering too much. I did it just to point some things out. But you notice like the tube. That's rolled metal that they had on the farm, maybe metal that was used in like a grain elevator. It's that size and that gauge and everything. So he found that. He got an old axle from a Buick car that his dad had. So he used that for the polar axis. There's little things on there like a garden hose handle that he used. There's an old metal pipe that he used for a handle. The base is from a cream separator. So you look at this thing, it's like a Frankenstein of telescopes. It's like all these different parts and pieces. There's no design for this, obviously. He just created it. And yet he made something that really will go down in history as a real important piece of astronomical heritage because of what he would do with it. But it's remarkable, I think, because he didn't let the lack of funding get in his way. He was creative and made this work. So he built this telescope out of all these parts, and then he starts using it. Again, during the daytime he's farming, at nighttime he sets it up on the and looks to the sky, and he gets very proficient at using it, and he continues to make drawings of planets, Mars and Jupiter especially. At that time he was able to see. And so he made a lot of drawings of it. And so this was his life for a year or so. He'd do the farming. He read all he could about astronomy. He'd set the telescope up at night. He would make drawings. And he's in his early 20s now, 21 or so, and still not sure what he wants to do with life, in his life. He'd love to go to college, but there's no money for that. So how can he make that happen? He's not sure. But he decides, maybe farming isn't the way he's going to do it, because there's a big storm and the crops are wiped out. And that's what really galvanized him to say, I just don't want to be a farmer and have to rely on the weather and the vagaries of that. I want to do something else. And why not astronomy? He loves astronomy. Why not get paid for what you like to do? And so he was in contact with the guy who polished his mirrors, or who did the final figuring, or I should say the initial cutting of it. He talked to that guy, and he offered him a job to come and help out. And Clyde was considering this, but he also decided to at this time, he had all these drawings, and he thought, if I'm going to go into astronomy, I wonder how good I would be. I'm self-taught. Those are professional astronomers out there that have gone to universities. So he decided to send some of his drawings to the pros, the people who would know. And when he was growing up and reading about astronomy, he was really interested in several different characters, but one of his kind of heroes growing up was Percival Lowell, the guy who in 1896 had built an observatory in Flagstaff, Arizona, specifically to look for intelligent life on Mars. And certainly in Clyde's day, and of course in today's day, we know that Lowell was wrong. There are no so-called canals on Mars, no intelligent life there. But Lowell had a way of inspiring people, even though he was wrong about some things, to inspire them to want to learn about the universe. And this really touched Clyde. And even though Percival Lowell had died years before in 1916, Clyde still knew about his observatory and knew that it was an observatory that studied planets. That was their specialty. So I'm going to send my drawings to Lowell Observatory to see what they say. And so he just, get their feedback. So he sends a letter, and he sends some drawings, and it ends up, the letter goes to this guy whose name is Vesto Slifer, or VM Slifer. And Vesto Slifer, at this point in his career, he was the director of Lowell Observatory. He was sort of in the middle, he was in the middle of his amazing career. His career actually, you could say, peaked a few years earlier because he was the first person to take really long exposures of spiral nebulae, as they were called at the time. Today we know them as distant galaxies. But Slifer, he was taking these long exposures for Percival Lowell years earlier to see if he could detect certain elements, to see if the elements, the signature of those would line up with the signatures of the outer planets. And so in doing this, Slifer took these really long exposures, like some more than 40 hours. So it's amazing. He would use the 24-inch refractor with a spectrograph on the end, slide in the glass plate, and when the object was up in the sky high enough, he would open the telescope and guide it for several hours until the telescope moved across the sky till the object was getting too low, close the shutter, and then the next night move the telescope back as the object came up, open the shutter again, and continue the exposure. Nobody had ever done this because why would you? This is a lot of time staring through a guide scope, and what was the end, even Vesto didn't know. But in doing this, he was able to pick up these really faint fuzzies, the spiral nebulae, and he also detected relative motion. Some objects were moving towards us, but most moving away. And it turns out that this was the first observational evidence of the expanding universe, the recessional velocity of these galaxies. So Vesto Slifer was very well known in the science community, had established himself. By the late 1920s, he was still doing research, but he was now director of the observatory. And as director, one of his projects was recommencing a search for what Percival Lowell called Planet X. Because Percival Lowell, when he wasn't looking for trying to prove intelligent life on Mars, he started looking for a ninth planet that he called Planet X. And he predicted a location and a relative size, and he continued searching for it until he died in 1916. And then that kind of ended the search. Well, in the late 1920s, the observatory, after being nearly broke after Percival Lowell's death, had new leadership, and they decided we have to recommence this search to find this planet, and that'll get us back into the mainstream of astronomy. And so Vesto Slifer is in charge of this project. And so this is what he's spending his time on when he gets this letter from Clyde Tombaugh, because VM Slifer has funding for a telescope, but who's going to do the observations? Because there's only 3 astronomers on staff, and they're all busy. They're all full-time. And so Vesto Slifer has been contacting colleagues around the country, asking if anybody has an assistant or has money to pay for an assistant. And this is what he's spending his time on, when one day he gets this letter from this guy in Kansas And this guy, turns out, was 23 years old at the time, Clyde Tombaugh. And this letter that says, "Hi, I'm a farmer. I love astronomy. I wanted to send you these drawings to see what you think." And Vesto Slifer says, this guy could be the answer to what we're looking for. We need a young assistant to be able to go in the telescope at nights during the right time of month to take the images, and then we'll analyze these images and look for this planet. So Clyde Tombaugh sends the letter off, and he gets the letter back from this guy, Vesto Slifer, that says, "What kind of physical condition are you in? Are you used to working long nights?" And Clyde was this was kind of odd. So they exchange a couple messages, and finally, after a couple letters, and I won't expect you to read this or anything, but it's this kind of long, rambling letter from Vesto Slifer that it ultimately says, "How would you like to come to work at Lowell Observatory?" And Clyde said, "Sure." And so in a few months, he arrives at the observatory. It's hard, it's easy to play that game of what if Clyde hadn't done this, would this have happened? If Clyde hadn't built that 9-inch telescope and sent the drawings, how would the search for Pluto have gone? They would have got somebody to do it, but it would have been somebody as detail-oriented as Clyde Tombaugh. It's hard to say. But the fact is, this is how it played out. They hired Clyde Tombaugh. He came to Lowell Observatory. He's 23 years old. He's self-trained, and he's going to help with this project to look for a planet. And so he helps, and he starts taking pictures, and then the senior staff is going to analyze the pictures, and soon they said, you can do this too, because this is really mind-numbingly boring, and we've got other things to do. So Clyde is soon using the 13-inch astrograph to both take the pictures on moonless nights, and then during the daytime, put these pictures on a machine called a blink comparator and analyze them and look for planets. Well, within a year of being at Lowell Observatory, Clyde discovered what we know today as Pluto. He's now 24 years old. And again, it's interesting to think his path to getting to Lowell Observatory that started with his passion, his ingenuity, his desire to work in astronomy, and because of that telescope he built out of his own mind, really, he got a job at Lowell Observatory, and at 24 years old, discovered a planet. I mean, it's a really great story, I think. So Clyde made his mark, and many of you have met him because of this discovery and his later work. So let's move on a little bit. The telescope has led us to this point. So what happened to the telescope after that? Clyde stayed at Lowell Observatory till the mid-40s. He discovered a planet, so he got a free ride to go to Kansas to get a degree. Worked at Lowell for several more years. Then he left to teach for a semester. And by that point, the observatory with World War II was out of money. And so they said, we can't pay you anymore. The program is done. So Clyde moved to New Mexico and went to New Mexico State, spent the rest of his career and, in fact, the rest of his life there. And so he taught many students. He used large telescopes, but he still kept his 9-inch telescope. That was his baby. It's not what started it all, but in terms of instruments, it really is what kicked off his career. And so even toward the end of his life, he would pull this telescope out occasionally and use it. And he would modify it over the years. At one point, he put a Coca-Cola can on the lens cap and added other things through the years. But this was Clyde Tombaugh's telescope. If you showed up at a star party with this telescope, everybody knew whose telescope this would be. And so he used it the rest of his life. Late 1990s, he lived a long, fruitful life, and he passed away. And so all of his stuff was left in his house, in his office. Clyde famously, in his office, both at home and at work, had piles of papers. And anybody coming in thought, how could you work in this pile that's as tall as he is? But he supposedly knew if you wanted a paper about a certain nebula, he knew which stack to go to and could find it. But for the family afterwards, after he passed away, there's a lot of stuff to go through. So it took years for for Annette and Al Tombaugh, the kids, to go through everything. And there are a lot of papers that went to New Mexico State and are now archived. So if you ever want to do research on Clyde Tombaugh between Lowell Observatory and the university, they have all of his correspondence. And then there was his telescopes. What to do with the telescopes? Well, Clyde's widow, Patsy, lived for several years and had some conversations with the kids about what do we do with the telescopes? Well, they knew there could be a problem with this because there were only 2 kids, but there were a lot of grandkids and other relatives. And it was clear that, if we leave a specific telescope to a specific person, everybody else might be a little bit tweaked about that. Somebody is going to be unhappy. And so in the will, she changed it to say all the telescopes need to be auctioned off and the proceeds will be split evenly among the family. Well, for the kids, for Al and Cheryl Lee, for Al and Annette, this was a little disappointing because this telescope in specific, they were hoping to just give to Lowell Observatory because of the connection and how this telescope got him the job and everything. And there were many other telescopes that he had. One of his that I think is really cool is the Gazer Grazer. He got a telescope and a push lawnmower, stuck the telescope on the push lawnmower, and that's how he moved it in and out of the shed at night. And so that was auctioned off, this one. But the Tombaughs had a special liking for this one because this is what started it all. But this is what the will called for and didn't want to split the family up over this. And so the Tombaughs spent several years looking for an appropriate auction house. In fact, they thought they were going to go with one in Europe, but the cost of transporting the telescope and the starting price of over $1 million that was going to be asked wasn't practical. And so finally, the family found a place in Texas, the American Heritage Auctions. And so last year, about this time last year actually, they took it down and prepared to have this telescope go on auction. And so at Lowell Observatory, our development team, our fundraisers, said, oh my gosh, this should be at Lowell. And a lot of people, I think, at the observatory thought that would be really great, but how do we get it? This isn't something you raise money for, it's an auction. But our development team said, let's talk to some of our lead donors, and if we can get a couple lead gifts, then we'll put a campaign out to where everybody can throw in a nickel or $1 or $100 or whatever to help get this telescope. So they did this, and they raised something like $120,000. And then it was the day of the auction. The Tombaughs went down to Texas. Our development team was on the phones. There was an opening bid of, I think it was $60,000. And so Lowell upped the bid. And then there was a lot of waiting, but ultimately the observatory won the auction. And we were able to get the telescope. And this was really, it was neat because the Tombaughs didn't know who got the telescope because that's private information. It wasn't until weeks later that, in fact, I was talking to Al and said, oh, we're so thrilled about the telescope, where it ended up. And Al said, where did it end up? And we said, Lowell Observatory. And so the Tombaughs were really happy, and we were thrilled to get it. It was shipped, I guess, in early June last year, shipped to the observatory in this big crate. And then opening it up was, these are several educators and other staff. It was, it was like Christmas. This is our telescope, and this is what it looks like. You can see it looks like a lot. It hasn't changed a lot through the years. Clyde painted it some interesting colors, and to balance it, it's really balanced. There's no locks on it. You can't lock it down in any way. So to balance it, Clyde had magnets that you could move up or down the tube, depending on how it was oriented. And so those magnets were all there. And so at the observatory, we decided, okay, this is going to be a showpiece. It's going to be a museum piece where people can learn about Clyde Tombaugh's early life, as well as what this telescope means to the history of astronomy. But wouldn't it be great to look through this thing once in a while? Especially, folks in this room, amateur astronomers who would really appreciate looking through this telescope. Wouldn't it be great to have it in working order? And so we decided, let's do this. Let's hire somebody to do this. And so we called up a guy named Ralph Nye, who some of you are into telescopes know. Ralph, he's in this picture here. Ralph is retired from the observatory now, but he's the one that led the renovation of the 24-inch refractor in 2015. And he also led the renovation of the Pluto Discovery telescope, the 13-inch astrograph. And so we said, he's the guy to do this. Look what he did with these other telescopes. And he said, he was licking his chops. He said, remember what we did with the Clark and the Pluto? That's what I want to do with this telescope. And this is where it got a little disappointing for him, because we said, we don't want to strip the paint. We don't want to clean it up. We want it to look like it was when Clyde used it. And so Ralph spent hours taking it apart, rebalancing it, doing the mirrors inside, but it really killed him not to clean it up and strip it. He did clean it, got rid of some rust, but this is what it looks like now. And yeah, he could have stripped it and made it look, shining and bright and everything, but it wouldn't have been Clyde Tombaugh's telescope anymore. It wouldn't have looked like it. I think the way it looks like right here, and we talked to our colleagues at the Smithsonian, and they agreed that we should keep it in, the shape that it was for Clyde. So this is what it looks like now. When you see it, this was that telescope. And you can see all the parts on it and everything. And even the lens cap has a neat story. The lens cap, when you took it off, there's a metal piece, and then there's a cardboard piece inside. And on both sides, there's all these hand-scribbled notes. Every time Clyde cleaned the lens from something like 1964 till the end of his life, he wrote it somewhere on here of the date that he cleaned the lens. So that was his method. So it's great for us because we have this, record in Clyde Tombaugh's writing of what he did. So we got the telescope, we got it renovated, and I think, part two of why this is so remarkable is, how this came back to the observatory through an auction. That's not how we get stuff, or, that's just so unusual. But there's so many people, I know some of the people in this room donated to the cause to bring the telescope to the observatory. And so the goal then was, we want to share it with everybody. When do we do this? And how do we do this? Well, every February, the observatory hosts an event called I Heart Pluto. And the I Heart Pluto Festival is a celebration of all things Pluto, and it's centered around February 18th, which is the date that Clyde discovered Pluto in 1930. And so what a great time to celebrate the telescope and to start sharing it with everybody. So in February of just a couple months back, this is when we unveiled it to everybody. So first of all, we had an event, and I think a couple people that I know a couple people that I've talked to earlier during NEAF were at this little celebration. So Ralph came in and talked about the renovation. And then we also took it out that night and did some viewing with it. And here's a young visitor. In fact, her mom is the head of education at Lowell, and she's looking through the telescope, just like Clyde Tombaugh did, and just like he did to make those drawings. So we opened it up for viewing, and then the next day, we had the mayor of Flagstaff come in and to formally designate it, and she designated Tombaugh Telescope Day in Flagstaff, and read a proclamation. And then we put it inside the Rotunda Museum, and this is where it's now on display, where you can come and see it. This is a picture of a really good-looking guy with an astronaut, Nicole Stott. Nicole Stott was the keynote presenter at the I Heart Pluto Festival. So we dedicated it and put it on display there. As a final thing to this telescope and this story, if you go to Flagstaff right now and go to a place called Mother Road Brewing Company, you can still get a can of still air beer, and it has that picture of Clyde Tombaugh with a telescope on it. And the reason they did that is in Flagstaff, it's a community that really likes its science and likes its astronomy. And it goes beyond the science. It's really a culture thing. And so Flagstaff sees itself as the home of Pluto and the home of Clyde Tombaugh. And so as we do this I Heart Pluto Festival, there's Mother Road Brewing Company. Every year, they create a specialty beer with a specialty can. And this year, we were telling the story about Clyde and the telescope, and the fact that to build it and to test it, he built that cellar so he could get still air. And they love the name still air, so that's why this is called still air. And one of the ingredients is passion fruit, to represent the passion that Clyde Tombaugh had for astronomy. So this beer you can still get. It's just a seasonal thing, but it's available in Flagstaff. So, it's just a really neat story, I think. And it shows I think the connectivity of Flagstaff and Northern Arizona, the amateur community with Clyde Tombaugh. That the world moves on. And, the story of Pluto is much more than its discovery, in the past decade plus with New Horizons, turning Pluto from a tiny dot to a world, and all the science that's coming out of it. The heritage of Pluto is so strong, especially in our country, I think. But to be able to go back to the beginning and look at Clyde Tombaugh's life and kind of how it all came to be, and the fact that it kind of started with this telescope that he built. It's kind of a neat story. So I appreciate you sitting here and listening to it. And if you get a chance to get to Flagstaff, it sounds like a commercial for visiting Flagstaff, and I guess it is sort of, but really it's a celebration of Clyde Tombaugh and his ingenuity. He didn't let a lack of money get in his way. He didn't let a lack of formal education get in his way. I think it's a great American story of hard work and dedication and not giving up. Like we heard from Eileen Collins yesterday, a desire to do something and making the sacrifices to make it happen. He's such a great example of that. And the telescope is a great example of what it takes. I think the telescope used to discover Pluto, the astrograph, that represents Pluto. This telescope represents the guy who discovered Pluto, Clyde Tombaugh, in his drive. So that's the story of Clyde Tombaugh's remarkable 9-inch telescope. I think it's a cool story, and it represents Clyde Tombaugh. So thanks for joining us today. And I think we can turn the lights on, and if anybody has any questions or anything to say about this, let me know. There go the lights. Yep, way in the back.
What's your question, but an interesting comment about Clyde Tombaugh and his personality. I met him in 1989. He was doing a book tour at the Adler Planetarium in Chicago. He even talked about packed auditorium, totally cool. And afterwards, we had a reception for him, and I had a couple images of Pluto I had taken, and I wanted him to look at it and sign it. So he looks at it, and I said, "Would you mind signing and putting your autograph on it?" The director of the planetarium was there, and he looks at us and he says, "No, Clyde has arthritis. He can't be signing any pictures." And Clyde says to him, "Don't worry about my arthritis. I'm signing this guy's picture." And he did it for me.
And that's Clyde Tombaugh. I think, I don't know, has anybody in here did anybody in here write Clyde Tombaugh? Write him a letter? There's one back there. I know a friend of mine, Bill Sheehan, who you might know from several of his history books. When he was younger, he wrote him, and he got this long letter back answering Bill's question, but also talking about what it was like to discover Pluto and everything. And it's just a great example of who Clyde was. He certainly got fan mail through the years, especially as he got older, I think, but he took the time to answer any letters. I think another thing that was neat about him, he grew up, the family had no money. They just didn't have any. And so again, the ingenuity, but he was from that generation that if they tore something down like a shed, they saved all their nails and pounded them back and straightened them and used them for something else. if he wrote a letter, it's interesting to look at correspondence that he has that's left over in New Mexico State and also at Lowell. A lot of the letters that he wrote to family members are in those archives, and there's no waste of space. He writes a letter, he's got columns, so he continues it on the side, then he goes on this side, then there's a little more space at the top. He didn't waste anything. And I think that explains kind of the pack-rat nature of his office, and that there's stacks of paper, stacks of everything else. He didn't get rid of anything, but he always had a use for stuff. And again, his ingenuity in using it. When you look at the telescope, like the magnets was brilliant, because when Ralph and I worked on rebalancing it, the telescope, you barely touch it and it moves. And so to use that for viewing with a lot of people would be very difficult, because we'll be resetting it all the time. And yet, by using those magnets, sliding the magnets up or down, you can balance it very precisely. And because the telescope doesn't move very much, he tried different ways of adding tension where the gears are. He stuck a wedge of wood in there, or later had sort of a bungee type thing to give some tension. So I think he was somebody that just kept tweaking and kept, trying till he made it work. Any other questions or comments? I think there's a hand up back here. Right. Yeah, the question relates to Pluto. All of the planets have a kind of a scientific symbol or abbreviation. They're not necessarily scientific, but they all have symbols. So Mars is a circle with the arrow pointing up, like the sign for males. And Venus is a circle with a cross pointing down, also the symbol for female. Well, for Pluto, when they were thinking of the name, after Pluto was discovered, they discovered it on February 18th, but the staff Lowell didn't announce it for several weeks because they wanted to make sure this is a planet and not something else. They wanted to study it and also ideally figure out its orbit. And so they didn't make an announcement for several weeks. I think another reason also is because Percival Lowell, who was, deceased by now, but in his lifetime, Percival Lowell, if he had a tidbit of anything, he would call the media. And I think the observatory was a little gun shy because they didn't want the media to say, okay, here's another Lowell Observatory thing, crazy, they have a new planet. So they want to make sure. So they rigorously studied it. And ironically, they know the position, so they went back on old photographic plates, and some plates from 1915 that were taken when Percival Lowell was still alive. Pluto actually shows up on a couple of those plates. They never found them until now because they're just these fuzzy little dots. So in Percival Lowell's time, he actually could have discovered Pluto. They imaged it, but he just didn't know it. But anyways, the observatory makes the announcement on March 13th of a new planet. And so they waited a few weeks to study it, but then when they decided to make the announcement, okay, we feel like we have it, let's announce it on March 13th. And for those of you into dates, March 13th, 1781 is the date that William Herschel discovered Uranus. So that was kind of a nice coming of full circle thing. But March 13th of that year also would have been Percival Lowell's 75th birthday. So what a great tribute to the guy who started the search to announce the discovery of this planet on this day. Well, after the announcement, the two big questions around the world from scientists, it was, we want to know the orbit. And from the rest of the world is, what are we going to call it? And there were names being sent in. The observatory still has about 250 letters and telegrams from around the world, people suggesting names. And one name, it's neat because you can look at these and tell the era, even if you didn't know the date, because some people suggested naming it after Charles Lindbergh, because just a few years earlier he had flown across the Atlantic, and so on. Several people suggested calling it Peace or Pax, which is peace, because the 1930s was designated as the decade of peace. It started off well, it didn't end so well in that. But then some other suggestions. The most common suggestion was Minerva, because Minerva was the goddess of knowledge, and they found this really, it had a lot to do with mathematically figuring out where to look based on the irregular movements of Uranus and Neptune. But Minerva had already been used to name an asteroid, so that wouldn't work. Another common suggestion was Pluto, because in mythology, Pluto is the god of the underworld, the most distant, cold region, and this planet was really far away. And so let's call it Pluto. And interestingly, several different people wrote in suggestions for Pluto, but the first person, the first letter we got, the observatory got, was from an 11-year-old girl in England. Her name was Venetia Burney. And apparently, the day that Pluto's discovery was announced, she was sitting at the breakfast table with her grandfather, and she had just been learning mythology in school and said, they should call it Pluto, because I learned in mythology that Pluto's so far away, and it also has siblings that I think Uranus and Saturn, that are in the solar system, so they should call it Pluto. So her uncle knew an astronomer. They sent a telegram to Lowell Observatory, and that was the first suggestion of Pluto. So she's kind of given credit with first suggesting the name. And so they named it Pluto. And then as a nice final touch, all the planets have symbols. So for Pluto, let's use a combination of its first two letters, P and L, which are also Percival Lowell's initials. So what a great tribute to Percival Lowell, who thought there was a planet out there. And so that's the symbol that it has today. And I think an interesting footnote to all that is that Percival Lowell predicted a planet was going to be out there. Pluto was really close to where he thought a planet should be, but Pluto is not his planet. He thought there was going to be a really big planet whose gravity would tug on Uranus and Neptune, causing them to wobble. Pluto is much, much smaller. Pluto is half the size of the United States in diameter. And so they looked very systematically, rigorously, and started where Percival Lowell thought a planet would be. They found a planet, but it wasn't Lowell's planet. They just happened to find Pluto right there. It's a great story, I think, that it was luck. You could call it blind luck. I mean, the work was systematic. If they hadn't found Pluto there, they would have kept systematically covering the sky. But they just happened to find Pluto right where Lowell thought it should be. It's another one of those things in science that is you scratch your head. You can't make this stuff up, sort of thing. Yes, sir. The satellites, yeah. Uh-huh. Right, the question was, where's the information about what Clyde Tombaugh did right after World War II? Because he was working at the missile, he ended up working at the missile range some, and used a converted telescope so he could track the missiles. And he even suggested painting a different color so we could see it easier. That's just now being documented, that work. There's a fellow named Bill Godbey who's in New Mexico, and if you give me afterwards, I can give you contact information. But Bill has written up some of that information, and if you go to White Sands Missile Range, today they have a missile display outside, and one of those things he uses on display now, and you can see that. So there's some stuff written up about that. Yeah, right. And so he spent several years doing that, and the chairs he used, I mean, they look like science fiction, he mounted the telescope on these things, and it's really neat to see it in person. If you do a search online, you can find a little bit of information too. But Bill Godbey is doing research on that. I don't know about that. Any other questions or thoughts? Yes, in the middle. The question was, whatever happened to Vesto Slifer? He spent the rest of his career at Lowell Observatory. So he started at Lowell in 1901. And in fact, he started on a temporary basis because Percival Lowell had promised a friend of his at Indiana University, Wilbur Cogshall, that he would hire this guy and for a few weeks maybe give him a trial. It turned out that the trial lasted for VM's entire career, but he made his big discoveries starting in 1912 when he did the recessional velocities, and then he continued doing that work for years. He officially retired in the 1950s, and in fact, upon his retirement, he donated money to buy tires for the old 24-inch Clark refractor. And if you've been to Lowell Observatory and been inside the dome and see it move around, it moves on 4 tires. That was a system that Vesto Slifer put in. So he died. Then he died in 1969. He lived into his 90s, and both he and his brother Earl, was also spent his entire professional career at Lowell and was a Mars expert. They're both buried in a citizen cemetery in Flagstaff. And their family still is connected with Lowell Observatory. For years, some of their kids were in advisory capacities and such. But Vesto kept doing research for a long time. He also bought a lot of real estate in town because during lean times, there wasn't much money coming in for salaries, so he bought a property and went into real estate and did pretty well with that. But I think he's another person that calls for a biography. William Graves Hoyt, who was a newspaperman that wrote several astronomy books back in the 70s and 80s, he started a biography of Slifer, but he died before he could finish it. But it's a pretty interesting story. And I think the connection between Slifer and Edwin Hubble, and Hubble used a lot of Slifer's work in synthesizing the expanding universe stuff. Yep. Any other questions or thoughts about a good place to eat in town? Yeah. Yep.
When Pluto was discovered, Pickering said, well, that's the same area of the sky that I had predicted Pluto would be. And when they came up with the symbol, PL, he said, what a great day this is. P&L, Pickering and Lowell.
Right. And William Pickering, for those, if you're not familiar with the name, his brother was the director of Harvard College Observatory. In fact, William Pickering helped Lowell Observatory in the early days. He advised Andrew Douglas of good places to do site testing, and then later at Harvard, he was searching for his own planet. And one of the neat things about that is Lowell was still alive, and Pickering said he talked about a planet O, and the comment was, yeah, O is right because there's nothing there. And that was their little dig at William Pickering. But that was an interesting, Pickering, because he searched for years, and he had not just one, but he had several different theoretical planets out there. All right, any other questions? I think that's it. Well, thanks everybody for coming in, and thanks.
Thank you very much, Kevin. Thank you. We'll be back for our next speaker at 2:45. Thank you.
We're very pleased to announce our new StarSense Explorer Dobsonians. The telescope tube features a larger aperture than the other StarSense Explorer telescopes. It also has a 2-inch Crayford focuser that accepts both 2-inch and 1.25" format eyepieces, and also has a custom pointing knob to help you precisely aim the telescope at your target. Both the tube and base have carry handles at their balance points, and of course, the exciting StarSense Explorer dock. Simply place your smartphone in the dock and launch the app. Choose from the best objects to view, then just move the telescope to follow the arrows to your target. When it's ready to view, the bullseye turns green. It's easy to do because of the patented StarSense technology.
Welcome to ZWO, the astronomical equipment brand that has been making astrophotography easy and fun for over a decade. Our founder, Sam White, established ZWO in 2011 with a mission to challenge traditional thinking and build an intelligent astrophotography ecosystem. Over the years, we have taken innovation and ingenuity as the key to our business growth, and years of dedication has made us a leading brand in the astrophotography market. Multiple of our camera models won the Hot Sky Product Award by the Sky and Telescope magazine in 2016 and 2017. In 2018, we released the game-changer ASI Air, a smart controller device that revolutionizes the way astrophotographers capture and process images of the night sky. In 2021, ZWO released the Harmonic Mount AM5, another addition to ZWO's ecosystem of astrophotography equipment. Every year, ZWO introduces more than 10 new products and brings new technology to the astrophotography field. With over 40 patents, including 2 pioneering invention patents, our company has been recognized with several prestigious titles by the state government that acknowledge our commitment to innovation and technological advancement. We also take great pride in our commitment to quality control and every aspect of the production process, from the initial design to material selection, testing, assembly, certification, and beyond, is subject to rigorous and meticulous control measures. This level of attention to detail is what sets us apart from the competition. At ZWO, we understand that creating outstanding hardware products is just one piece of the puzzle when it comes to providing a streamlined astrophotography experience. That's why we are equally committed to developing cutting-edge software products that work seamlessly alongside our hardware offerings. The ASI Studio is an all-in-one astrophotography software platform that is specifically tailored to work in tandem with ZWO cameras and provides a range of functionalities, including planetary imaging, video stacking, DSO imaging, live stacking, simple post-processing, bits files preview, and more. The ASI Air mobile application is tailored to the specific needs of astrophotographers, providing an integrated workflow including camera control, mount control, EAF control, precise focusing, auto run, post-processing, and many other functions. With our ASI Mount mobile application, users can effortlessly take control of their mount using mobile devices, eliminating the need for hand controllers or being tethered to the mount. It is the shared love for astrophotography that unites us all and drives the ZWO team to continue pushing the boundaries of what's possible. Together, we have traveled across the country in pursuit of the perfect shot of the night sky, leaving footprints from the picturesque landscapes of Dali and Guilin to the rugged terrain of Daosheng, Dunhuang, Inner Mongolia, and Xizang. We believe that by immersing ourselves in the natural beauty of our surroundings, we can gain a deeper appreciation and understanding of the universe we seek to capture. Moving forward, ZWO remains committed to its mission of making astrophotography easy and fun for amateur astronomers worldwide. Our goal is to enable enthusiasts of all levels to explore the wonders of the universe with ease and precision, so they can focus on what matters most, discovering the beauty and mysteries of the cosmos. To empower and inspire everyone's journey in astrophotography.
We're very pleased to announce our new StarSense Explorer Dobsonians. The telescope tube features a larger aperture than the other StarSense Explorer telescopes. It also has a 2-inch Crayford focuser that accepts both 2-inch and 1 1/4 format eyepieces, and also has a custom pointing knob to help you precisely aim the telescope at your target. Both the tube and base have carry handles at their balance points, and of course, the exciting StarSense Explorer dock. Simply place your smartphone in the dock and launch the app. Choose from the best objects to view, then just move the telescope to follow the arrows to your target. When it's ready to view, the bullseye turns green. It's easy to do because of the patented StarSense technology.
If you were asked to visualize a typical astrophotography rig, what would it look like? This was how things have looked since the launch of ASI Air in 2018. And this is how it looks now. Thanks to the continuous innovation and new technology ZWO brings to the market, with the latest additions to its lineup, this rig is packed with all the gear you'll need to capture breathtaking images of the cosmos. Introducing the ASI 2600 MC Duo. that seamlessly integrates the imaging sensor and guiding sensor into one powerful device, needing only one cable, which reduces potential cabling issues and greatly improves setup speeds so you can spend less time on preparation and more time on capturing the beautiful universe. The 1/1.8-inch guide sensor taken from the ASI 220mm mini camera combined with the IMX571 from the ASI 2600MC provides stunning performance even when guiding using a 7nm duo-band filter in good sky conditions. A rotary knob controls guide sensor focusing, designed to simplify the process of making two sensors both in focus in one optical system. This combination of guide and imaging sensor in one camera creates an imaging solution that ensures both sensors parfocal over long periods of time, which reduces complexities by removing the need for a separate guide camera and off-axis guider. Duo does it all. And this is the all-new ZWO Astrograph from the FF Apochromatic Refractor series. This series features a flat-field Petzval quadruplet design with two ED glass elements offering excellent control of chromatic aberration. The ZWO FF series APO refractors create beautiful-looking stars. RMS radius at the center of the field of view can be as small as 2 nanometers, perfect for both visual use and astrophotography use. Differently from normal refractors, the self-flattening design of ZWO FF series does not require a specific back focus from the rear lens, providing freedom to use any filter wheel, any off-axis guider or accessory without the worry of calculating the correct distance from the flattener. ZWO's matching reducers widen the field of view, offering a new perspective from your telescope, and with reduced image capture time. Still, 55mm back focus distance must be maintained when using our reducers. The rigid dual-speed focuser comes with a new type 360-degree rotator with scales and a finder base, making focusing easy and quick. Matching with ZWO EAF, the electronic automatic focuser, it will bring an incredible using experience. The new ASI Air Plus 256G offers an increased eMMC storage space and improved performance from the ZWO custom compute board. With short exposure, the total imaging efficiency will be improved by about 26% compared to its predecessor. The FPS on video mode also improves by about 30%. And finally, we are proud to introduce our new AM3 mount. The new high-performance harmonic mount offers astrophotographers exceptional performance at an even more affordable price. It carries a payload of up to 8 kilograms with no counterweight, and up to 13 kilograms with the addition of a 5 kilogram counterweight. The newly added Bluetooth unit makes wireless connection without hand controllers possible. Carry less. Capture more. Enjoy yourself under the starry night sky. To empower and inspire everyone's journey in astrophotography.
It's great to be here. Thank you. Wow, there are a lot of you.
Welcome to ZWO, the astronomical equipment brand that has been making astrophotography easy and fun for over a decade. Our founder, Sam White, established ZWO in 2011 with a mission to challenge traditional thinking and build an intelligent astrophotography ecosystem. Over the years, we have taken innovation and ingenuity as the key to our business growth, and years of dedication has made us a leading brand in the astrophotography market. Multiple of our camera models won the Hot Sky Product Award by the Sky and Telescope magazine in 2016 and 2017. In 2018, we released the game-changer ASI Air, a smart controller device that revolutionizes the way astrophotographers capture and process images of the night sky. In 2021, ZWO released the Harmonic Mount AM5, another addition to ZWO's ecosystem of astrophotography equipment. Every year, ZWO introduces more than 10 new products and brings new technology to the astrophotography field. With over 40 patents, including 2 pioneering invention patents, our company has been recognized with several prestigious titles by the state government that acknowledge our commitment to innovation and technological advancement. We also take great pride in our commitment to quality control and every aspect of the production process, from the initial design to material selection, testing, assembly, certification, and beyond, is subject to rigorous and meticulous control measures. This level of attention to detail is what sets us apart from the competition. At ZWO, we understand that creating outstanding hardware products is just one piece of the puzzle when it comes to providing a streamlined astrophotography experience. That's why we are equally committed to developing cutting-edge software products that work seamlessly alongside our hardware offerings. The ASI Studio is an all-in-one astrophotography software platform that is specifically tailored to work in tandem with ZWO cameras and provides a range of functionalities, including planetary imaging, video stacking, DSO imaging, live stacking, simple post-processing, bits files preview, and more. The ASI Air mobile application is tailored to the specific needs of astrophotographers, providing an integrated workflow including camera control, mount control, EAF control, precise focusing, auto run, post-processing, and many other functions. With our ASI Mount mobile application, users can effortlessly take control of their mount using mobile devices, eliminating the need for hand controllers or being tethered to the mount. It is the shared love for astrophotography that unites us all and drives the ZWO team to continue pushing the boundaries of what's possible. Together, we have traveled across the country in pursuit of the perfect shot of the night sky, leaving footprints from the picturesque landscapes of Dali and Guilin to the rugged terrain of Daosheng, Dunhuang, Inner Mongolia, and Xizang. We believe that by immersing ourselves in the natural beauty of our surroundings, we can gain a deeper appreciation and understanding of the universe we seek to capture. Moving forward, ZWO remains committed to its mission of making astrophotography easy and fun for amateur astronomers worldwide. Our goal is to enable enthusiasts of all levels to explore the wonders of the universe with ease and precision, so they can focus on what matters most: discovering the beauty and mysteries of the cosmos. To empower and inspire everyone's journey in astrophotography.
We're very pleased to announce our new StarSense Explorer Dobsonians. The telescope tube features a larger aperture than the other StarSense Explorer telescopes. It also has a 2-inch Crayford focuser that accepts both 2-inch and 1.25" format eyepieces, and also has a custom pointing knob to help you precisely aim the telescope at your target. Both the tube and base have carry handles at their balance points, and of course, the exciting StarSense Explorer dock. Simply place your smartphone in the dock and launch the app. Choose from the best objects to view, then just move the telescope to follow the arrows to your target. When it's ready to view, the bullseye turns green. It's easy to do because of the patented StarSense technology.
If you were asked to visualize a typical astrophotography rig, what would it look like? This was how things have looked since the launch of ASI Air in 2018. And this is how it looks now. Thanks to the continuous innovation and new technology ZWO brings to the market, with the latest additions to its lineup, this rig is packed with all the gear you'll need to capture breathtaking images of the cosmos. Introducing the ASI 2600 MC Duo, that seamlessly integrates the imaging sensor and guiding sensor into one powerful device, needing only one cable, which reduces potential cabling issues and greatly improves setup speeds so you can spend less time on preparation and more time on capturing the beautiful universe. The 1/1.8-inch guide sensor taken from the ASI 220mm mini camera combined with the IMX571 from the ASI 2600 MC provides stunning performance even when guiding using a 7nm duo-band filter in good sky conditions. A rotary knob controls guide sensor focusing, designed
Coulihan.
Hey, thank you. All right, thank you, everybody. Thank you. So our next speaker will be done virtually due to the fact that he could not travel under doctor's orders, but he will be done virtually. Fred Hayes is a retired NASA astronaut, a former Marine Corps fighter pilot, and the United States Air Force test pilot. He was one of 19 astronauts selected in 1966. He served as the backup lunar module pilot for Apollos 8 and 11 and was the lunar module pilot for Apollo 13.
only service I could get into to become an officer, which was what my dad encouraged me to do, was the Naval Aviation Cadet Program, which obviously would involve flying airplanes. And I had never been in an airplane in my life, not even sitting in one on the ground. So at 18 years old, I signed up. And of course, what happened is I enjoyed and loved flying from the first day I flew, and decided that's changed my career. So somehow the rest of my life and career was going to be involved with aviation. There was no space program at the time. So that was a right turn in my career path that led to eventually getting involved in Apollo.
You also were a Marine fighter pilot, and you were also a test pilot. And, that's basically you're on the right track to becoming an astronaut. But I understand that Neil Armstrong visited Edwards Air Force Base, correct me if I'm wrong, while you were there after his Gemini mission. And I was wondering if he had an influence on you applying to the astronaut program.
Yes, in a way. I started as a test pilot, actually, not introduction set Air Force. I was actually a NASA test pilot, which we call ourselves research pilots, at Lewis Research Center in Cleveland, now named after John Glenn, and moved to Flight Research Center, you mentioned, at Edwards, which is now named Armstrong after Neil. And Neil started the same way. He started at Lewis, and he then went to Edwards, got to fly the X-15, which I didn't, before going into the astronaut program. And he visited back home at FRC one day, and Don Melick, another pilot, and I talked to him and kind of asked him, what's it like being an astronaut, Neil? And his response kind of set me back a little bit thinking about it, because he said, you sit in a lot of meetings, you sit in a simulator lots and lots of hours, and there's no good flying. And of course, he was talking about our experience flying almost every day, involved in several research programs at the same time back at NASA FRC. And so it really didn't hype me up to immediately become an astronaut, but I looked over my situation, and I'd hoped to fly the X-15, which is really the last spacecraft that's been manually flown the entire profile, to launch, over the top, and entry. It's the last manned aircraft that's been flown that way. The rocket, you're just a rider and hoping that you don't have to abort. And so I really hoped to get into that program, but realized our office kind of operated by seniority within your time in the office. And I was about 2 down the line, and thought I'd never get to fly the X-15 before the program ended. So that's what encouraged me. If I'm going to get higher and faster, the way to do it is in the astronaut program. And actually thinking about it, going to the moon sounds pretty exciting.
Yeah, that would sound pretty exciting to me as well, yeah. And of course, you were on the backup crew of Apollo 8 and 11, and I believe 16. But I think what most people don't realize is that you're on the background, you're on the backup crew, and you were trained just as if there was a failure or someone couldn't go on that flight. And I think it was you, Buzz Aldrin, and Neil Armstrong on 8. Is that correct?
Buzz and I were 8. I actually filled into an opening that had resulted in Mike Collins having a medical problem, and he got moved off he would have flown 8. And he got moved out of the alignment, and Jim Lovell moved up. So Jim ended up flying on 8, and that opened up a spot for me. So that was, I was the first one in my group to get a crew assignment as the lunar module pilot on 8 with Neil and Buzz.
And Andy, if I could, before you go too much further away from his test pilot years, you might have Fred talk about his experiences with Chuck Yeager and how he was invited as a NASA research pilot to enroll in the test pilot program. And he got to do something that non-military people don't really get to do.
Well, what he's talking about is I had a chance to fly Chuck on a chase mission to observe one of the launches of the first lightweight lifting body. We were flying a program of vehicles, and it ended up being four version 5 of the vehicles ultimately flew with rocket engines, but were without wings. They were called lifting bodies. And Chuck was due to fly the first one we built, which was a lightweight version, which was towed behind a DC-3, basically. It was an Air Force C-47. And so I took him on a flight in a T-37 aircraft to show him how the flow would go through that launch, to that launch point. And on the way down, the only way in the T-37 you could keep sort of in alignment with the M2 F1, it was called, and a steep dive to the landing was just before separation. I knew I'd shut off one engine, put speed brakes out, and put landing gear down, and at the release, shut off the second engine. So I had both engines shut down, and then still was overtaking the M2 and had to do barrel rolls around it a couple of times to create drag enough to back up, in essence, and fly alongside the lightweight, and landed without ever starting the engines, and had enough energy to roll over to the ramp that went up by NASA's hangar, and parked in the same spot I had left without ever starting the engines. And that impressed Chuck. I think that's why he later offered me to go into the Aerospace Test Pilot School, ARPS it was called, and at the time, and I was the first civilian to ever go into that school. And interestingly, Chuck had not officiated it till they got to go on a trip to, we're going on a trip to Europe. And I told Chuck that, since I wasn't officially in the class, I'd just go back down to NASA and wait till they got back. And he just casually said, no, it's about time I told those people in the Pentagon you were in the school. So I got to go through the 1 year in the ARPS Air Force Test Pilot School during that time.
I also understand, of course, you're a lunar module pilot, and I understand that you spent quite a bit of time here at Grumman on the development of the lunar module.
That was my first assignment after the rookie training, which went on about the first 7 or 8 months. And I was assigned to Jim McDivitt, Ed Mitchell, and I, and a system engineer named Dave Ballard. And we went in to see Jim McDivitt. He was slated to fly the first LEM and test it in orbit, LEM 3, or LEM 2 at the time, actually. And we went to his office, and Jim had very simple orders to Ed and I. He said, I want y'all to go to Grumman and make sure I got a good LEM to fly. So that was it. That was the total instructions. So I spent the next 14 months, most of it at Grumman, testing not just LEM. It turned out LEM 2 got pushed aside because after the fire, where we lost the crew on the launch pad, there was severe wiring constraints imposed. And LEM 2 was so far along, we'd have had to strip it to start over almost. So we jumped to LEM 3 to be the first one in orbit. LEM 2 was then made a backup for the LEM 1 unmanned flight, with the thought that the wiring, taking the risk with the wiring wouldn't be that bad if it was just a backup unmanned vehicle. So that's how LEM 2 ended up in the Smithsonian in Washington. But at any rate, that was my first assignment, and I did spend, incredibly, the Grumman reflected the workload and schedule pressure throughout the program, when in the book I describe in 1967, test operations, testing lunar modules, getting ready to get shipped to Kennedy, went 24 hours a day, 7 days a week. We only planned one shutdown that entire year, Christmas Day. And that was pretty much the way it was if you'd gone to North American with the command module, or subcontractors who were struggling to meet delivery schedules with their components. And that was pretty much across the program at that time, trying to meet the schedule to land on the moon by the end of the decade.
Well, I have to say, I've known you for quite some time, Fred, and you always have a smile on your face, but when I see you at a Grumman event here at the Cradle Aviation Museum, I always see a bigger smile. I know you spent quite a bit of time here. I guess would like to talk about Apollo 13. I'm sure everybody's really interested in Apollo 13. Lots of 13s if you're superstitious on the mission. Of course, Apollo 13, and I guess it was launched on the 11th of April at 13:13 Central Time, and the explosion was on, I believe, the 13th of April. But who's superstitious, right? The mission, I understand, was going well for a couple of days. You were going to do a live broadcast back to Earth, and that was the first time that was done from the module. It's right from the command module.
Right.
Tell us a little bit about that.
Right. We did a show and tell kind of thing from the lunar module. Yeah.
Oh, from lunar module. Okay. Yeah.
And it so happened the timing of that when Jim Lovell ended the program and signed off. If that program had been 30 minutes longer, we would have been on live TV when the explosion happened. Because they called at that time, they called Jack Swigert to stir the cryos, and we had the Big Bang. And think we had a very interesting couple hours after that, trying to get things settled down, to get the LEM powered up. Did quite a bit of troubleshooting for almost an hour in the command module before ourselves and Mission Control had run out of ideas, and went to get the lunar module powered up as a survival, to have communications and environmental system to live off, and propulsion availability till things slowly got figured out as we went down the road from there.
How long did it take before you just figured out the whole problem, from the time that the explosion to the time you realized that, hey, we're not going to land on the moon?
Within the 1 minute after I drifted up from the lunar module into the command module and looked at the instrument panel, from several readings, it was clear we had lost oxygen tank 2. Without reference in mission rules, I knew that constituted an abort. And so I just was sort of half sick to my stomach at that time. I'd trained to go fly 2 missions, and now was my big chance. And I knew we would not even go in the lunar orbit, much less try to land on the moon.
Yeah. At that point, what was the decision made to just to slingshot around the moon instead of turning back? Why was the decision made to go around the moon, come back, instead of just turning around and coming back?
Well, that was made by obviously a meeting of some of the flight directors. By that time, Glenn Lundy had come in and joined Gene Kranz, and Chris Kraft and others counseled, and so they made that decision. That rather than try to use the SPS engine, the big engine on the command module, but we really didn't know the total damage at the time, they would elect to buy time, really, to work things out by changing the path to go around the moon.
So at this point, when was it decided that you would use the lunar module as your lifeboat?
Well, that was decided probably about a little over 50 minutes after the explosion, and that was kind of the point at the end of the troubleshooting. That's when Jim and I left the command module, left Jack alone, and we went to power up the lunar module. So we were already on that new path, really after a little over 50 minutes after the explosion, to live off the lunar module, whatever we're going to have to do to get home over the next 4 days.
And I'm sure that power and water and things like that were certainly the things that you were very dear about, as far as how much you had left. And so what was your biggest challenge, as far as was it power, was it food, was it water?
No, the oxygen was never a problem. We had lots of oxygen with just the tankage and the descent and the ascent stage of the LEM. Plus, we had 2 full backpacks that we're going to use for our EVAs. And each backpack had a 6,000 PSI emergency oxygen bottle in case you had a slow leak in the spacesuit while you're out on EVA to get you back in. Each of those was about 1 day's worth. And so oxygen was not a problem. Water was only a problem mainly for cooling. cooling whatever equipment we had on, which lived off cold plates, electronics, and not for drinking. That was never a problem. The biggest probably was electrical, because the LEM only had batteries, 4 in the descent stage, 2 in the ascent stage. And the ascent stage batteries were smaller. So that was a critical commodity. And Jim, after the first maneuver we did using the landing engine on the LEM, the one we landed with, to put us on the path to go around the moon, he asked me to compute consumables, which I did manually on using a cue card. And burn card, we called it, and figured we at the time we would run out of water probably a few hours before the planned entry, which was 150 something hours at that time. But I'd make it on the batteries, and I assumed the power down to about 18 amps on the 30-volt system. And I wasn't worried about the water, because on Apollo 11 we'd asked Neil and Buzz to shut off the water valve on their LEM, and we watched the equipment die. And the first critical equipment, if anything, died at about 8 hours. And I figured I'd run out at about 5. So I said, maybe I got some pad there even. But then we did the second maneuver after passing the moon that cut 10 hours off the return. So that made us even a little fatter on consumables and reserve.
Yeah, I understand that you, I think this came from Mission Control, but there was a little magic played here. You had the lithium hydroxide cartridges that didn't fit. They fit in the command module, but not into the lunar module for you.
Now that was something at least I wasn't even aware of. That was a pending problem. The ground Mission Control on their readings picked that up quicker and had people going to work on that, particularly Ed Smiley's group. Crew Systems group, and he led that division, and Bill and Seven at Johnson. And they fabricated a canister, a prototype, and tested it actually in a chamber. They happened to have a small chamber that had the LEM environmental system in it. And they put that device in there, hooked it up, and actually impregnated the chamber with a lot of CO2 and verified that it would work. And before they then had to write meticulous step-by-step procedure to pass up to us to fabricate. And I was not involved, actually. I was off duty at the time. Jim Lovell and Jack Schweigert actually built that canister fix. They called it the mailbox. That did the job.
Yeah, I understand that it was duct tape, socks, and cardboard that was used to make the fix.
Correct. There was cardboard was really the hardbacks of books, checklists, and socks were used to plug the hole in the center of that square cartridge from the command module. In fact, 2 socks were pushed in there, and had cellophane material that was from clothing we had vacuum sealed, and it wasn't delicate material. You had to use scissors to cut it. So unlike the movie, it had me involved in ripping it. I was never involved even. But it was tough material. Again, the gray duct tape we had on board was used for that. Now, duct tape, incidentally, was primarily on board with the thought of cleaning the filters on the environmental system. And for dust and particles that may have evolved on the filter, you could rub that duct tape on it to clean it off. So that was one of the main reasons we had that on board.
Well, one of the, I think I might have forgotten to mention for our audience here is that what are the lithium hydroxide, what do they do to, their purpose was really important purpose, right? Is correct? As far as changing carbon dioxide back into oxygen?
Yeah, well, it got rid of the carbon dioxide. It had the lithium hydroxide material in the canisters, both the LEM one, which were round or cylindrical in shape, and the command module ones that as you pass air through it, would capture the carbon dioxide. And so it would cleanse the air. And like I said, we never had any physical effects, although it was inching up toward the red line in the cabin, but we never had any effects. And the cartridge, of course, did the job it was intended.
So when was it decided for you to get back into the command module? And I know that there had to be quite a challenge because I know what I wanted to the temperatures in the lunar module, because I recall the temperature being very cold, you had told me.
That was a critical part of the mission, and that never has been covered very well, and certainly it was not available. The kind of thing would have been covered in media in any way. You have to realize the command module, the mothership, that we had to completely shut down for 4 days, and the water tanks froze in that vehicle during that time. They were found still frozen when they recovered the capsule on board the aircraft carrier and inspected it. Water tanks were still frozen. And so there was the main thing is there was not a procedure to turn it on, to activate it, because nobody ever figured we'd have to activate the mothership in flight. And they did not pass that procedure up, which I'll have to say was a great job by many people that got it, first of all, written down. Then other astronauts, people tried it in simulators to redline it, I'm sure, several times, I was told, and get it right. That was a critical thing to have that procedure right, because it was something we had never done before. And obviously, if we're going to have to do something like that, we would have gone through that dozens of times in a simulator before the flight. But Jack copied it. They read it up to him at about 17 hours. 17 hours before we were going to enter the air, whistling in at 25,000 miles an hour. Because of the limited power in the capsule, command module, they were not going to allow us to start the power up until 2.5 hours before we hit the air. Primarily because the command module only had 3 small 44 amp hour entry batteries that were necessary to get us through entry for control, get the parachutes out, etc. And so they didn't want to use up any more of those batteries than they had to getting through that power up. So they delayed us to that time, and Jack and I went into the command module. Dark, it was dark, we had to have flashlights. And first noticed water covered the instrument panel, all the instruments. So Jack got out 2 towels, and we each wiped off the instrument panel so we could see the meters. And we started into that checklist. The first step was to push in a bunch of circuit breakers that were on 2 panels, one on each side of the spacecraft. And Jack thought about it. He's again thinking of the Apollo 1 fire and all that water hanging around. He knew it was probably behind the panels as well, worried about electric shorts. They said, "I'll tell you what," he said, "I'll give a call and we'll push in any row only 6 circuit breakers and stop and wait a little bit and see if we smell wiring insulation burning." So that's the way we went through getting all the circuit breakers in, and that went through. And we were saved, really, I'll have to say, we were saved by the Apollo 1 fire, because the accident investigation, one of the things done was that severe wiring protocol that was opposed, including hermetically sealing all the wiring at all the connectors. And so virtually we had a waterproof wire harness. Otherwise we would have made it from probably right there with electric short. So that went smoothly, and we shucked the limb not about 45 minutes before hitting the air. Sort of canted out and yaw sideways to make sure it got clear and didn't impact us during entry. And everything went fine. We had a little rain shower at the top of the entry where some of that water started falling out as we hit the air. But otherwise, it was what I'd call a perfect entry, pretty much tied, I think, for the second most accurate splashdown of the program.
It's that was I wanted to mention about the temperature also that you had in both the lunar module and the command module before that.
Yeah, the limb was a little warmer because we did have some of the electronics on, and of course all 3 of us huddled in there most of the time, so we had our body warmth. But obviously with the water tanks having frozen in the command module, it was sitting right at freezing or a little below. The limb was probably in the mid-30s to high 30s most of the time.
Bill, what were your recollections when this was all happening? I remember when I was pretty young at the time, but listening to the whole thing in the media, what do you recall at the time when you were listening to all this with the media?
Well, one thing that I think everyone can relate to is the movie Apollo 13 and how gripping it was and edge of the seat the movie is. And it seems like it's one of those movies you can watch anytime you're going through the channels and it's on. But honestly, the real deal was a lot more gripping, a lot more edge of the seat, because you didn't know from day to day. And of course, we had 3 different networks that covered it at the time, and each one had their own, spin on what was going on, and it was quite a time. I was like the crew. I was really upset that we weren't going to have a moon landing, and then of course it quickly turned to concern for their safety and getting them home. So it's a pretty special time. And when you talk about the movie Apollo 13, they got it right most of the time. It was a pretty accurate film, but Fred will tell you there are a few things they had to do. What did Ron Howard tell you, Fred? Something about it wasn't dramatic enough with the mission controller lingo that was going on.
They had to add some drama in here and there to humanize us.
Well, Jerry Griffin's here. I think he should really be doing this other than me, but he knows that well, much better than I did about the drama, of course. And
hi, Jerry.
Hi, Jerry. I think maybe the best thing is to open up some questions for everybody. Anybody like to ask questions? We have anybody? No? Oh, here we are. Yes. Stand up and speak as loud as you can. What did you do in your spare time when you were in the command module or the lunar module when you were coming home?
Most of the time, it was the spacecraft. We never could get the so-called PTC, where you revolve it in like a barbecue mode to have it hot and cold alternately around the spacecraft. And we were just kind of slowly tumbling, if you will, in various directions. And occasionally you'd get a view of the sun, Earth, or moon. And most time I was just looking out the window at views in between the next thing to do. The way we shifted for the first 2 days is I would be on alone, and Jim and Jack would then cycle that way. And then, of course, by then it really got chilled down slowly to the temperature I mentioned, the 30s. So we normally all 3 stayed in the LEM all the time. And another interesting side bit is Jack Swigert, the command module pilot, had never been in a LEM till that flight. He was like me at Grumman. He was spending his time at North American working the command and service module. He was the expert on that vehicle. And it was funny when this all happened and we left Jack to power down the command module alone and to power up the LEM. He showed up finally, and I noticed him behind me there. He perched down, came through the tunnel, and sitting back on the Asin engine cover, the engine that would have lifted us off the moon had we landed. And Jack's only comment was, he said, "Do you think this thing will make it?" I said, the LEM is a pretty fragile vehicle compared to the command module for the weight requirements. It had no inner wall. It had netting material that was up to keep you from bumping in to the wiring harnesses and to plumbing that you could see all around the vehicle. You could see through that netting. And it was loud. There was very little insulation, no insulation. So the pump sounds, the glycol pump, and then it had a habit of gurgling occasionally and changing frequency, whining. And the cabin fan was loud, so it was very noisy compared to the command module. So that made Dak nervous for a little bit, to worry if the lunar module was okay and it was going to keep running for a few days.
Another question? Okay.
When you landed on Earth, what were your thoughts? What were you thinking then?
When we splashed down, well, obviously very, very happy to make it back and grateful for what had been done, which was kind of out of the box, so to speak, thinking and working hard. And incidentally, many people I talked to, obviously, about what went on, found that many probably got less sleep than I did on board. With the timeline they were given by Gene or Glenn Lundy or one of the flight directors, Jerry Griffin, to come back to them with answers, they probably got less sleep than I did. Didn't even go home. I understand some of them just slept in mission control, even on the floor, to get things done when they got too tired to think straight. But not time enough to feel they had to go home.
One more, couple here. Anybody can bring the mic over? Stand up. Maybe it's easier. Who has the mics?
I got one.
Right here. There are a couple people right here.
That's all right.
You speak about the entire experience in a very calm and concise manner, and I know that there were things that had to be done and whatnot, but natural human instinct would have you, as I would think, being very frightened and questioning whether or not reentry would be successful. Can you describe how you felt at that time?
Well, I mean, the thought of whether you survive or not is before you go. Kind of even from fighter squadrons I was in the Marine Corps and in the Air Force, a normal thing was you had your best friend as a designee that would take care of your wife and family. And so one day you didn't get back. And it was the same way. I had Jerry Carr, who was a neighbor, a Marine, as I was, had been a former Marine, over to my house even to show him where paperwork was and that kind of thing. So he had the primary responsibility, if I didn't get back off Apollo 13, to be I call it the key person, at least worry about the administrative things for the wife and family. Of course, she'd have a lot of support from other astronaut wives and other astronauts that would be at the home, as they were throughout the flight, as well as NASA had a protocol officer there to handle anything needed. So that was just normal business, if you will, not just traveling in space, but it was in my career as a fighter pilot and as a test pilot for NASA.
Anybody here?
Was the mid-course direction, or was the mid-course correction as dramatic as shown in the movie?
No. We did two of those. There actually was one of those done on Apollo 9. It was one of their test objectives. They did the same manual maneuver. Now, they used a different alignment way, but the actual burn itself and the control of the vehicle was done on Apollo 9. We had to align it a little differently. Jim used the COAS, which is your sighting, normally sight on stars or something. I call it, it's like a gun sight, out his left front window. And he could sight on the Earth, which was actually roughly a half Earth and the cusp of the Earth, and aligned on that, and then they were directed us this procedure, and then pitched up slowly. And I was looking through the AOT, the optical telescope, and the lunar module, and the upper point of view in that instrument was at 60 degrees up. And when I saw the sun just peer into that view of that instrument, I called Jim to stop the pitch rate. So he froze the vehicle in that point. Now, at this time, we had the abort guidance system up, which is a very smaller even than the command module system, which incidentally, our big computer and the guidance nav and control system we had, a hand-wired core, was like 1/10 of a megabyte. I said megabyte, not gigabyte. And so the computer was smaller in the abort guidance system, so we could afford to briefly have it up. And we could issue one command that would give us 2 needles on our instrument in front of us, that if we kept those needles centered, controlling pitch, yaw, and roll, would hold us in that attitude that we'd just frozen at. And so that's what we used for controlling. And the way we did it was with two people. The configuration we were in with the limb still attached to the much heavier command module. We had to use the translation control left and right for roll control, and the translation control fore and aft for pitch control. And the little hand controller you normally use was only good for yaw, which went pretty much straight up through the axis of the two vehicles together. So when we started to burn, I would control pitch, pushing or pulling on the translation controller, and Jim would do roll using left-right commands. As it turned out from the data the ground collect afterwards, I looked at it in a graph chart. We did not deviate much more than a degree in any axis. And of course, as you said, the movie had us about going out of control. The burns were very short. One was a little over 20 seconds using, I think, the decent engine. And the other one was 18 point something seconds using the 400-pound reaction control jets in one direction for that burn. So they were very short maneuvers.
Not like Tom Hanks in the movie.
Yeah, thank you. That's saying some of that, Jim Lovell hugging me, my exaggerated throw up with space sickness. Jack and I arguing about who threw the switch, that kind of stuff. That was what he's called humanizing, because Ron told me he listened to all the air-to-ground transmissions that NASA had provided, and he said it didn't ever sound like you had a problem. So he said, I had to humanize you in some way. So that's with some of those things.
Anyone else? Any questions? Some people in the back.
Hi, thank you for talking to us. I was wondering, when you look back on the mission itself and its role in your life and the space program, would you choose to land on the moon, or would you choose to go through the whole ordeal if you were doing it again?
Oh, I'd like to land on the moon, obviously. I have to tell people I've developed neuropathy in my feet, and I look kind of funny in my spacesuit trying to get around the moon with now my three-wheel walker I use quite a bit. I wouldn't quite have the right look.
What kind of lessons from Apollo 13 do you think could be learned by the the Artemis program coming up? And just what are your thoughts on Artemis 2 coming up? They're going to be repeating the free return trajectory on their mission, although it'll be a nominal part of their trajectory. They're not aiming to land on the moon, but yeah, your thoughts on these new upcoming moon missions.
I don't really have any thoughts about a direct thing that would apply that hadn't already been applied from the axe investigation they did on 13 on, follow-on spacecraft like Space Shuttle, et cetera. Their whole mission approach is different. We launched on one rocket and had both spacecraft aboard. I think their mission involves the launch of, not their launch, but the later landing missions involve several launches. They have this lunar orbiter that's a fairly large orbit around the moon, a stable orbit, I think 6 days. Around the moon, they have a service module, effectively, that's produced by a European Space Agency. So it's a totally different approach and the things involved to affect the landings. And part of it, I guess, came about because of the thought of eventually, hopefully, going to have a lunar base where they would be better suited to logistically support that situation. That kind of drove, I think, to the architecture they ended up with in this case, rather than ours, which was just to land, stay a short time, and collect samples and come home. So that directly, even the mission planning, it's a whole different ballgame. I have not been involved directly in NASA's technical shop. I do a lot of work with the education department for children and teacher events. But no, I'm glad to see they're going back. The first flight, some people complain it's not ambitious enough, but it's a build-up thing you try to do in testing. They're going to do a thorough systems test of certainly the capsule that's not been done, and as they did kind of on Apollo 7, to make sure it's in good shape, and the booster, of course, that gets them out there, and the other propulsion systems involved to tweak the path and the trajectory to get them back to entry and through landing.
I might add a little bit of trivia here. Apollo 13 has had the record for that furthest point out in space when they made their loop around the moon, headed back to Earth. All the other missions went into lunar orbit, so they didn't go as far. And they'll have that record until Artemis goes, and they'll go a little bit further out and break that record from 1970.
We have a youngster here who has a question.
What was it like when the mission started?
What was it like when a mission started? You're talking about launch?
Yes. Yes.
And the Saturn V?
What was it like when the mission started? You know, I'm sure at launch.
Oh, at launch?
Yes, at launch, yes.
I'll say one difference was I don't think I was excited as emotionally as I'd seen. I had been on the so-called closeout crew, one of Gunnar Vent's 6-person group who got the astronauts aboard and strapped in and ready to go and close the hatch and check the seal. I had done that for Apollo 8 and 11, so I was the last one out of the capsule. And both times I had to crawl underneath and come out from below to get out the hatch to close it before they left. And I could see they were really pumped up and ready to go on both 11 and 8 and 11. It was somewhat damped because we had done that crew changeout. We had worked with Ken Mattingly through the Apollo 11 back up, and now we're trained to go fly 13. And at the last minute, 2.5 days before launch, they pulled Ken off the mission because of the measles threat, and Jack Swigert replaced him. Incidentally, unlike the movie, we didn't fear Jack's ability to fly the mission. As I said, we trained equally, prime and backup. You could have changed out the whole crew the week of launch, and it wouldn't have mattered. The mission would have gone. But it was just sad to have, because mentally the two, and I had that experience as a backup, you get really excited with 4 or 5 weeks before launch. When you're the prime, you're now, man, I've got all this way and I've worked hard and I'm finally going to get to fly. And you see sometimes the booster lit up on the launch pad at night. So you're really hyped up and getting excited to go. And on the other hand, as a backup, at that time, I sort of mentally backing off from that thought, because I knew I'd have to just go watch somebody else fly, even though I'd done all the same work. So you kind of mentally back away. So that now is a flip-flop for those two people at that short time, 2.5 days before launch, to change those roles. And the same way I felt sad that Ken had been removed from the crew, not from worrying about a technical issue or worrying about performance on the mission. So that was one thing. The ride itself, the only describe it as unusual from my airplane flying, which I obviously had a lot under my belt at that time of many different types of aircraft and situations. The 4 engines on the Saturn V, the big engines, gimbal left and right, fore and aft, to control the rocket's path. The big engines, 7.5 million, about 7.5 million pounds total, about 1.5 million each. And when they moved even a little bit, you got a lot of motion, feeling that motion up, because you were sitting way up on the top in the capsule, up at the top of that 360-something foot rocket. And particularly unusual was the left-right motion, because the couches were fastened in the overhead in the capsule, but had a little clearance on the side, because they were built to have you some cushioning on splashdown, or even if you had to make a landing and then aboard. And so they were allowed to move, and you got a lot of left to right herky-jerky, I'll call it, motion when the rockets gimbaled in that direction. That was pronounced and quite different from anything in an airplane. Airplane I experienced, as most of you in the audience probably have that flown airliners, you get in the turbulent air and you get a lot of bouncing up and down. But you don't get too much left to right as motion swinging in the seat. And that was what was most unusual. The G levels were modest compared to what I'd experienced in fighter airplanes, which even in my day were good for about a little over 7 Gs, and the first stage only got to 4.5. And modern fighters, of course, can pull up to 8 or 9 Gs. So, the G level wasn't that terrific.
Time for a couple more questions.
In the movie Apollo 13, during the live broadcast, it shows you turning the cabin repress valve. Is that something you guys did? And if so, what was that used for?
The cabin repress valve was kind of the closeout and a procedure you had for the LEM environmental system. And I can't describe physically why, but it made a bang sound. And I had done that, not in flight, but I had done that before in like a chamber test we did. And so that was what was referred to, and Jim was hoping at least that's what had happened that caused the explosion. As it turned out, I had not done that at that time, unfortunately. But that was just a thing that normally, if you were courteous, you would have warned people you were going to throw the valve, so they'd be ready to experience that and not think something was wrong.
Hi, I worked many years at Grumman, including the years that you were there, and we've crossed paths there. Many of the people, as you know, many of the engineers worked on Apollo when they were in their 20s and 30s. And when they were in their 40s and 50s, they looked back and said that was the highlight of their career. What's your opinion about your Apollo experience? Was that the highlight of the career, the years that followed? How would you rank things?
Well, I certainly say I feel blessed to have been around at the time. I was just thinking back to the last century. And if you think of what the greatest things to influence the USA at least, our country, was the 2 world wars, obviously, and the 2 programs, development programs or exploration programs that stand out is the work that was done on the program to invent the atomic weapon and the Apollo program. Both were struggling with schedule pressure. Tremendous schedule pressure. And those stand out as the biggest things in that century. And I was just happy to think back now and say, wow, I was born at the right time and got to the right age with the right credentials and experience to be a part of it. As far as personally thinking of it as a test pilot, my greatest experience was the approach and landing test. Primarily because I left the astronaut office and spent 4 years in the orbiter project office in program management with Aaron Cohen, who's the project leader. And so I was very involved with the early design development for 4 years of orbiter specifically, which I had not been involved in design at all in Apollo. It was already designed and I was more in the vehicles being manufactured and ready to ship stage of that program. But I was there from day one on shuttle. And now after 4 years, I got to go back to the astronaut office and named to command Crew 1 with Gordon Fullerton, Joe Engel, and Dick Truly were Crew 2. So the 4 of us were going to fly an 8 test flight program where we're going to use the 747 carrier aircraft as our launch vehicle. That could get us up to a little over 25,000 feet at release point and do testing as a glider without engines on the way down to landings at Rogers Dry Lake at Edwards Air Force Base in California in 1977. So that first launch was I look back and say that was the greatest event of my experience in time as a test pilot. There was a lot of pressure on that flight. I was concerned because we had got to a point in the program where, number one, there were slips and delays, particularly in the orbital flight announced from problem with the tiles on Columbia. And a new president had arrived. Jimmy Carter had come in that January. The program was started under Richard Nixon, so it was his program. And we were concerned about how President Carter might feel about continuing and to what degree. And I was worried if I did something wrong and crashed Enterprise, that could end the shuttle program right there, because we did not have a backup vehicle. That was deleted for cost very early in the program. So as I climbed the ladder that morning to get aboard, that was reflected by the people on the ground who had managed to shoot a photo of people wearing blue suits like we were wearing and their helmet on, same helmet we were wearing, and with a visor down and oxygen mask hanging so you couldn't tell who the people were. They're sitting on this huge sweeper that sweeps big city streets. And the saying on a little card by the picture said, "If you screw this up, this is your next job." So the workers were worried about how this flight was going to go as well.
Time for another question or so. Anyone? Right here, maybe?
Sir, we're glad you came back safe and everything is good. Just one question. When you and your crew were on the dark side of the moon, the furthest human beings away from the planet, how lonely did it feel to be in the great big black of space by yourselves?
I didn't feel lonely at all. Jack Swigert and I had cameras out. We had film to burn. You know, we're going to have all that lunar orbit time that Command Module used those cameras. We had black and white cameras, Hasselblads, and color. And Jack and I were shooting pictures furiously of everything in another direction. We had a broader view of the surface on the backside. It was about a half. Incidentally, it's not the dark side of the moon unless it's a full moon. People get to think of always the dark side being dark. I think a lot of people in this audience know that's not quite true, but some people in the general public think that. So we had a half moon, and but from a higher altitude, we were about 132 miles up. Had a broader expanse to shoot pictures of. Shot very good pictures of Moscow and Tsiolkovsky on the backside. That our lunar trainer, Farouk Albaz, praised us after the flight for those pictures. I think he was trying to make us feel good. That we'd done something good on the mission anyway. And so that's what we were busy doing. Jim was not. He was severely disappointed. I can understand. That was Jim's second time to the moon. He had gone on 8, and now he was going to land on the moon, and it fell out for him. Now, I didn't know at the time, but hoped I'd get a second chance, which I thought it was when I trained 16, backed up John Young. I thought I was going to get to fly 19. But of course, within about 4 months in that training cycle, 18 and 19 were canceled. So I did not get my chance to go back.
We have time for one more? I'm sorry? Oh, okay. So, but I have to say one thing with Jerry here. Unlike the movie Apollo 13, there was more than one flight controller in mission control. You only showed one.
Yeah, definitely.
Well, that explains why Jerry Griffin wasn't at our anniversary event night before last. I was at Gilroy Center with over 200 of his compatriots. Gene Kranz was there, Milt Winland was there. And so he missed seeing some of his old buddies along with me at that event at Johnson Space Center night before last. Great event.
We're glad to have him here, that's for sure. Yeah. Well, we're sorry that you couldn't make it, but thanks for being with us. And in closing, Ladies and gentlemen, Bill Moore, author, and American hero, Fred Hayes.
Thank you. Enjoyed talking, everybody.
Thanks.
Welcome to ZWO, the astronomical equipment brand that has been making astrophotography easy and fun for over a decade. Our founder, Sam Webb, established ZWO in 2011 with a mission to challenge traditional thinking and build an intelligent astrophotography ecosystem. Over the years, we have taken innovation and ingenuity as the key to our business growth, and years of dedication has made us a leading brand in the astrophotography market. Multiple of our camera models won the Hot Sky Product Award by the Sky and Telescope magazine in 2016 and 2017. In 2018, we released the game-changer ASI Air, a smart controller device that revolutionizes the way astrophotographers capture and process images of the night sky. In 2021, ZWO released the Harmonic Mount AM5, another addition to ZWO's ecosystem of astrophotography equipment. Every year, ZWO introduces more than 10 new products and brings new technology to the astrophotography field. With over 40 patents, including 2 pioneering invention patents, our company has been recognized with several prestigious titles by the state government that acknowledge our commitment to innovation and technological advancement. We also take great pride in our commitment to quality control and every aspect of the production process, from the initial design to material selection, testing, assembly, certification, and beyond, is subject to rigorous and meticulous control measures. This level of attention to detail is what sets us apart from the competition. At ZWO, we understand that creating outstanding hardware products is just one piece of the puzzle when it comes to providing a streamlined astrophotography experience. That's why we are equally committed to developing cutting-edge software products that work seamlessly alongside our hardware offerings. The ASI Studio is an all-in-one astrophotography software platform that is specifically tailored to work in tandem with ZWO cameras and provides a range of functionalities, including planetary imaging, video stacking, DSO imaging, live stacking, simple post-processing, bits files preview, and more. The ASI Air mobile application is tailored to the specific needs of astrophotographers, providing an integrated workflow including camera control, mount control, EAF control, precise focusing, auto run, post-processing, and many other functions. With our ASI Mount mobile application, users can effortlessly take control of their mount using mobile devices, eliminating the need for hand controllers or being tethered to the mount. It is the shared love for astrophotography that unites us all and drives the ZWO team to continue pushing the boundaries of what's possible. Together, we have traveled across the country in pursuit of the perfect shot of the night sky, leaving footprints from the picturesque landscapes of Dali and Guilin to the rugged terrain of Daosheng, Dunhuang, Inner Mongolia, and Xizang. We believe that by immersing ourselves in the natural beauty of our surroundings, we can gain a deeper appreciation and understanding of the universe we seek to capture. Moving forward, ZWO remains committed to its mission of making astrophotography easy and fun for amateur astronomers worldwide. Our goal is to enable enthusiasts of all levels to explore the wonders of the universe with ease and precision, so they can focus on what matters most: discovering the beauty and mysteries of the cosmos. To empower and inspire everyone's journey in astrophotography.
We're very pleased to announce our new StarSense Explorer Dobsonians. The telescope tube features a larger aperture than the other StarSense Explorer telescopes. It also has a 2-inch Crayford focuser that accepts both 2-inch and 1.25" format eyepieces, and also has a custom pointing knob to help you precisely aim the telescope at your target. Both the tube and base have carry handles at their balance points, and of course, the exciting StarSense Explorer dock. Simply place your smartphone in the dock and launch the app. Choose from the best objects to view, then just move the telescope to follow the arrows to your target. When it's ready to view, the bullseye turns green. It's easy to do because of the patented StarSense technology.
If you were asked to visualize a typical astrophotography rig, what would it look like? This was how things have looked since the launch of ASI Air in 2018. And this is how it looks now. Thanks to the continuous innovation and new technology ZWO brings to the market, with the latest additions to its lineup, this rig is packed with all the gear you'll need to capture breathtaking images of the cosmos. Introducing the ASI 2600 MC Duo, that seamlessly integrates the imaging sensor and guiding sensor into one powerful device, needing only one cable, which reduces potential cabling issues and greatly improves setup speeds so you can spend less time on preparation and more time on capturing the beautiful universe. The 1/1.8-inch guide sensor taken from the ASI 220mm mini camera combined with the IMX 571 from the ASI 2600 MC provides stunning performance even when guiding using a 7nm duo-band filter in good sky conditions. A rotary knob controls guide sensor focusing, designed to simplify the process of making two sensors both in focus in one optical system. This combination of guide and imaging sensor in one camera creates an imaging solution that ensures both sensors parfocal over long periods of time, which reduces complexities by removing the need for a separate guide camera and off-axis guider. Duo does it all. And this is the all-new ZWO Astrograph from the FF Apochromatic Refractor series. This series features a flat-field Petzval quadruplet design with two ED glass elements, offering excellent control of chromatic aberration. The ZWO FF series APO refractors create beautiful-looking stars. RMS radius at the center of the field of view can be as small as 2 nanometers, perfect for both visual use and astrophotography use. Differently from normal refractors, the self-flattening design of ZWO FF series does not require a specific back focus from the rear lens, providing freedom to use any filter wheel, any off-axis guider or accessory without the worry of calculating the correct distance from the flattener. ZWO's matching reducers widen the field of view, offering a new perspective from your telescope, and with reduced image capture time. Still, 55mm back focus distance must be maintained when using our reducers. The rigid dual-speed focuser comes with a new type 360-degree rotator with scales and a finder base, making focusing easy and quick. Matching with ZWO EAF, the electronic automatic focuser, it will bring an incredible using experience. The new ASI Air Plus 256G offers an increased eMMC storage space and improved performance from the ZWO custom compute board. With short exposure, the total imaging efficiency will be improved by about 26% compared to its predecessor. The FPS on video mode also improves by about 30%. And finally, we are proud to introduce our new AM3 mount. The new high-performance harmonic mount offers astrophotographers exceptional performance at an even more affordable price. It carries a payload of up to 8 kilograms with no counterweight, and up to 13 kilograms with the addition of a 5-kilogram counterweight. The newly added Bluetooth unit makes wireless connection without hand controllers possible. Carry less. Capture more. Enjoy yourself under the starry night sky. To empower and inspire everyone's journey in astrophotography.
It's great to be here. Thank you. Wow, there are a lot of
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
All right. All right, thank you all. Before we begin with our keynote speaker today, I had 2 announcements. I want to first of all thank all of you for being here at NEAF 2023. It wouldn't be a success without all of you, so a big shout out to all of you. Thank you so much. And secondly, I'd like to have a round of applause for those that made NEAF 2023 happen. You have Ed, Mies, Karen, Sarah, Joe, Frankie, Keith, and all the volunteers. There's a lot of volunteers here too. A big round of applause for them. Thank you all very much. Our next speaker is a graduate from Texas A&M. He's also a commissioned officer from the United States Air Force. He served as a flight controller at NASA, joining NASA in 1964, supporting the Gemini program. In 1968, he moved as flight director for all the manned Apollo missions. In 1982, he succeeded Chris Kraft as the director of the Johnson Space Center. Please help me welcome to NEAF, a true American hero, Jerry Griffin.
Thank you, Vinny. Hello there. Well, I sat in the audience and watched Fred Hayes. I'll try to straighten out all the mistakes he made. And I'm just kidding. He was mostly right. When Karen asked, we started talking about me appearing, and I was going to be the in this case, the last speaker, I tried to think of a subject that would just kind of wrap this whole thing up. And so I called it Where We've Been and Where We're Going. And I'm not going to rehash a lot of the stuff that you've already heard from other speakers, but you'll see a little of it. I'm going to talk a little more about the people and what it was like and how much we had to put into it to get out of it what we had in mission control and in space and elsewhere. So where did all this begin? It's important, I think, that we remember there's two kinds of flights. There's robotic flight, and then there's human space flight. They're both very important. In robotic spacecraft already for years, we've had a lot of Department of Defense, and I'm not going to read all of those, but you can read them for what they've been used. On the civilian side, it is extremely busy in that community. And it looks like that there will be a sustained growth in both of these categories, both DoD, Department of Defense, and also for the civilian side. We heard some earlier about that, and boy, some exciting things going on. So it's not an either or. That's important to remember because quite often people in the human spaceflight business get accused of not caring for robotics and vice versa. And that there may be a little of that, but it's minuscule. What they do with robotics facilitates and actually makes human spaceflight possible. Now, having said that, I don't want you to think I'm going to turn my back on it, but I'm really going to focus on human spaceflight today because we've only got a short period, and I could talk for days on the robotics. Where it began, some people say, well, it began 13th century when the Chinese figured out how to take their firecrackers that they had made and make them propulsive and shoot arrows with them. That's probably a pretty good definition of the beginning. A more recent one happened in Germany, a beginning during World War II. And up there at the little red spot at the top is Peenemünde, where they developed the buzz bomb, which was not really a rocket, it was a pulse jet. But they developed the V2 rocket. The Germans developed that rocket, and it only flew toward the end of the war. Had that been earlier, it's possible the outcome of particularly the European campaign, would have been much different. But it was the first time liquid fuel rockets had been put and used for a purpose. There had been some experiments, but that was about it. I think the modern beginning, of course, was Sputnik, flown in 1957 by surprise by the Soviet Union. About a 2-pound ball, weighed a couple 100 pounds, chock full of electronics. Those 4 antennas that come off of there actually was just transmitting a beep, 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 beep. But it absolutely shocked everybody in the world that they had that capability. Everybody kind of swung into action in the Western world quickly. We responded a few months later with this Explorer 1, which actually Van Allen was one of the principal investigators of this thing, and that's where it actually discovered the Van Allen radiation belt that goes around the Earth that we try to stay away from because it's high radiation. But at least we answered with something in orbit, which was good. And then they surprised us again. The Soviet Union in 1961 launched Yuri Gagarin into orbit on a Vostok, which looks very much like the Soyuz of today. I think they just like that design, basic design. That really set us back. So what happened next? JFK, President Kennedy, went before the Congress in May after he had flown in April, after Gagarin had flown in April, and announced that he thought we should go to the moon and take a man, he used that term, put a man on the moon and return him safely to Earth. We hadn't even put anything in orbit yet, human-wise, and so he set this goal to go on to the moon. Pretty gutsy. So there was our goal. The moon, roughly half the diameter of Earth, and it's 240,000 miles away. And it varies because it's not in a perfect orbit around us. But that was a big task. I can remember when that happened, I was just gotten out of the Air Force, and even I thought, I'm not sure we can do that. When I got to NASA, I found out that there were a lot of people that thought the same thing. Can we really do that in this decade? Since we're starting from zero. But actually things started happening in a big hurry. The Mercury program was a one-man, really kind of taught us the idea that we could put a person in orbit and get them down. They were strapped in so tight that they couldn't do much, but it worked. That led us to Gemini. Gemini was a two-person ship, and that was the key to the success of Apollo. Because with Gemini, we learned how to rendezvous, how to dock, how to do a spacewalk, an EVA, extravehicular activity. NASA always had those long words. And so it really enabled it. We also flew a mission long enough to go to the moon and back in Gemini, just in Earth orbit. So we knew that people could withstand that time in space. And then finally, Apollo. Now, there's one point to make about this chart, and that is that I consider Mercury Gemini part of the Apollo program. They were all step. And we called Mercury the Mercury Project, or Project Mercury. We called Gemini Project Gemini, and then we called the Apollo program Apollo program. I really think they were all together. It was just phases of getting to the moon. The sequence went like this. We launched the Mercury spacecraft, launched first on a Redstone missile, so small it could not put a capsule in orbit. But we did lob two guys about 300 miles down the Atlantic from Cape Canaveral and got them a few seconds of minutes even of weightlessness, but that was about it. But it did prove that we could do something. When we went to the second booster, that was the Atlas. It was the first time that we had a booster with liquid oxygen and liquid hydrogen as a propellant. And it had a lot more oomph in it. And indeed, we put 4 times we flew Mercury, and the first time was John Glenn, who was the first American in space. Then we flew Gemini on Titan. It was bigger and could get this heavier spacecraft into orbit. And you can see we flew that thing a bunch, and boy, were we moving fast. I was in mission control for all of the Gemini flights, and they were absolutely back to back. We were launching about every 6 weeks. That was unheard of today, but we were kind of in a hurry. And then the Saturn V came along, and that was our Germans, the von Braun and his key people that we got. The Soviet Union got the others when Germany fell, and we got von Braun and several of his key people. One more thing on this. These photos are not to scale. The Saturn is a lot bigger than that redstone. And I've got the heights on there, but the Saturn was completely different than anything else. But one of the things to notice, those first three were all ICBMs. Actually, the redstone was what they call an intermediate, but the others were Atlas and Titan were intercontinental ballistic missiles. They could carry a warhead, big one, and the Cold War was raging at this point. And we were trying to outdo the Soviets, and the Soviets were out trying to outdo us. So, had we not had that capability, and those rockets had been around a while, we would have been in deep stuff early on. But we had those rockets that they modified to make them a little more man-rated, a little more forgiving, double redundancy, and that kind of thing. When we got this Apollo, we stumped our toe coming out of the gate. We had the Apollo 1 fire. Now, that's quite often referred to as Apollo 1. It's also in the old days, it was AS-204, Apollo Saturn 204. And the 204 came from the booster number. After the fire, the system was renumbered, and in honor of the crew, we named that first one where we had the fire on the pad, Apollo 1. We went to work. We were down for almost 2 years of that 9 years we had to go. And we worked almost 2 years. It was about 21 and a half months. And we launched Apollo 7. So they get 1 to 7. In between were all of the unmanned booster flights, tests, without people. And that's why they put those right after 1. But 7 was the first manned Apollo mission. And it was the same mission, basically, that we had planned for Apollo 1. A few changes. There were a few changes in there. So the Apollo 7 was followed by what I think is the gutsiest call NASA has ever made. And it was Apollo 8. A human being, had never ridden on a Saturn vehicle. And that last test flight, 6, had 2 major problems. It was a Saturn V. The center engine cut off in the second stage, and then the third stage, the S4B, called the S4B, did not restart, and that's what you needed to do, translunar injection, to send you on your way to the moon. The people at Huntsville and Marshall Space Flight Center, who were dandy, by the way, Von Braun was then the center director. They said, we know what caused both of those, and we can fix them, and we think you can go. We didn't have a lunar module ready, so we took just the command module and these 3 guys and put them in it on top of a Saturn V and launched them very near Christmas of 1968. And boy, was that a gulp moment when we did TLI, translunar injection. That said, now we're into it. Now we got to get them back. And in these early missions, we didn't try to do a lot. We tried to make sure the transportation system was working. Even when we got to the moon early on, we kind of got the science, whatever we could get out of it. Our focus wasn't on the science, our focus was on the transportation system. That changed later. I'll talk about that. Apollo 8, this was the first time that they had seen a Earthrise. And Bill Anders, by the way, an old buddy of mine, we were in the same fighter squadron before there was a NASA. And never did we think that we would line up and collide again in the business. But Bill Anders was the lunar module pilot. I always kid him. He was a lunar module pilot on a mission and didn't have a lunar module. And so we circled the moon on Christmas Eve. But they saw this Earthrise, and Bill immediately said, "I got to give me a camera." He was at the right window, so they finally got him a camera, a color camera, and Bill said something when he got back I thought was profound. We went to explore the moon and discovered the Earth, and that's a little bit of the theme of the people thought that all of the crews of Apollo mentioned, that every time they looked back at Earth, they were amazed how small it looked and fragile. And Jim Lovell always talked about, I can put my arm at length and cover it up with my thumb. He said it made you really realize kind of how small in this complete universe and galaxies and all of that, how it was. But everybody he knew, he said, was still on that Earth, and other than the two guys that were with him. So I think it was a profound moment for the guys. So the hardware and the software were ready. The mothership, the command and service module, I'm going to talk about that in a second because I'm going to hit something on Apollo 13, not vast, but the lunar module was ready. The Saturn was ready. The crew was ready. And then everybody else, the launch control people at Kennedy, who never have gotten the coverage and the ink that they deserve. Massive job. And boy, they did it, and they still are doing it. And they launched Artemis 1, same family. Mission Control in Houston was ready. We had a global tracking network that had it not been for the Air Force, we wouldn't have had. They allowed us to put our people into our own consoles that we installed there. And so we had these sites around the world. We didn't have satellites yet that would give us full coverage of communication coverage. And then, of course, all of the contractors that built the hardware, and it was July now. A piece about kind of what I want to center on mission control here. But if you notice at the top, the spacecraft and mission control, we got way too much of the coverage and the joy and the attention by the media, particularly. And we kept trying to throw some of it at us. Hey, we got this great support system underneath us. And you can see the number of people. The Department of Defense was incredible with their tracking stations and recovery forces with a carrier and helicopters and frogmen and so forth. So I created this to give you an idea. I think it was like an iceberg. And like I say, the tip was sticking out. And you heard from Mission Control because Capcom was talking to the crew and the crew was talking to us. And when I was a flight director, we worked around the clock, so we had shifts. After every shift, there was a press briefing by the flight director. I don't know how many I did, and it had all the major networks. Even if it was 2 or 3 o'clock in the morning, a few of them would show up or send somebody. And so it was mission control and the astronauts. And there was so much more behind us that we couldn't have done without. There was no way we could do it all. But everybody thought we could, so I guess we kind of let them think that a little bit, but not much. And boy, did we ever start riding that Saturn when everything was ready. We always include one. There were 12 Apollo missions, and they went in a sequence left or right by row. There's that Apollo 8 that I think is the gutsiest call we ever made. This was, by the time we got here, the first landing, we really did have, we had a much better understanding of what we had and what we had to work with and what, the idiosyncrasies and the surprises that you would get in any new system. But in the lower right-hand corner, that finally came to an end. We went out to the moon 9 times because 2 of these missions that are shown here, Apollo 7 and 9, were intended to be in Earth orbit from the beginning. 10, Apollo 10, was we called it a dress rehearsal. And a lot of people say, well, why couldn't you land on 10? Well, we couldn't land on 10 because the lunar module was too heavy. Starting with 11, there was a second block of lunar modules that were much lighter, had been trimmed down, all the kind of the test stuff taken out of it. And then so 11 on, we could land. So we got out there 9 times. Of course, we had the 2 that we didn't intend to land on, 8 and 10. And then on 13, we intended to land but didn't make it. But we did do a lunar flyby. But that all good things came to an end. Those last 3 missions, we had a rover. I can tell you by that time, we were focused on the science. Why were we going there, not can we get there and get back? So it was a change that, and I think Artemis is going to go through the same thing. They're going to have to make sure that everything works before they start spending a whole lot of time on science. Now, they can get what they can get early like we did, but they got to be careful in those early flights because they're going to have some surprises. The landing sites, we landed 11 in one of those gray areas, which is a mare, M-A-R-E, is an ocean, pretty flat. And all we wanted Neil and Buzz to do was to get down and land. And of course, where they were, the computer was taking them was full of boulders, not very big, but well, big enough, tall as that chair. So he had to extend the landing and go on down range. That's why he got so low on fuel. Notice how near the equator that is. 12, we went over to a place called Ocean of Storms, a little more rugged. There happened to be a surveyor spacecraft that had been launched about 2.5, 3 years earlier, a robot that was sitting there. And we wanted to see if we could get close enough. A pinpoint landing was our point. And we did. When they looked out the window, Pete Conrad said, guess what I see? I see the surveyor. It was about 600 feet away. So they went over to it and got parts of it and all of that. 14 came back to Fra Mauro. That's where 13 was going to go and didn't make it. This was even more rugged. But notice how close to the equator. And there's a reason for that. This is the farthest away from the equator on 15 at a place called Apennine Mountains, Hadley Rill. And the reason we couldn't get very far from the equator is we didn't have the performance to do it. We didn't have enough propulsion. And there's a reason for that if you look at the flight dynamics of what you got to do to get to the lunar surface. So we were kind of limited to our target area. 16, we went down to a place called Descartes, very rough, with some huge boulders. One of them they found was what we call the house boulder. It's big, big as a house. And then 17 ended up going up to Torres Litro in a place with a very, very rugged. And but think about that equatorial kind of alignment. And the reason is that Artemis is shooting for the poles. And they say they're going to do it on the first landing. I don't know whether that is, well, I don't know whether it's too smart because it's going to be tough. It's very dark down there. There are craters that have never seen the sun. The sun angle is so big. The bottom of the crater. And orbiters have found ice in them. So the presence of water on the moon. And we're going to do that eventually. I'm just saying maybe the early flight Artemis 3 ought to land up in that one of those mares where it's pretty flat and make sure everything's going to work. I laid those landing sites out, in this case on Europe, and you can see it doesn't cover a very big area. It goes from northern Germany to the boundary of Portugal and Spain. If you put that on the United States, it goes from about where we are here on the east to Arkansas, close to Arkansas, and Michigan and South Carolina on the north and south. Not a very big area. So you can't really say that what we did in Apollo was did we explore the moon? We explored a little of it. That's it. And we haven't done anything on the backside with humans. So 17 ends, that's Gene Cernan giving a final salute before he got back in. You can see the rover right behind his backpack in the lunar module with the American flag. And right after that, he got back in and came home, and that was the end of Apollo. I want to make this, I said I wanted to talk about the people and what this was like. And that's a picture of the Mission Control Center. I know more about this than any other place in the center, in the agency, so I'm going to talk about it. It's the Christopher Kraft Mission Control Center. That's a picture of Chris Kraft and me. I succeeded him as the center director at the Johnson Space Center. And you notice this was at the splashdown of STS-5, fifth shuttle flight. And Chris decided to retire. I was the deputy director at Kennedy by this time, and they asked me to come back to be the director of Johnson Space Center. There I was, my first flight, Apollo 7, and first manned flight. As a flight director, I was 33. Notice the haircut, crew cut, okay? Here are the 5 flight directors that did, 5 of the 6, there were 6 of us actually did all of Apollo, but there were 5 of us that took on Apollo 11 since it was the first landing. And actually I was assigned with the guy sitting in the very front, Cliff Charlesworth, on the first shift. There's our ages. We had gotten a little older because we'd gone through Gemini now, but we were still young people. And we were the oldest people in the room. We had 21s, 22s, 23s. And in fact, in Gemini, we were younger too, but the average age was 27. So you think about what we were trying to do, and I think they intentionally went and got some people that didn't have a lot of bits set in their brain how things ought to be done. They had to listen and adapt to going to the moon rather than flying test airplanes. There's Apollo 13 splashdown. That's me in the front with a cigar hanging out of my mouth and a book of matches in my left hand with my thumb in the air. And I lit that cigar right after we waited. We never celebrated when the capsule hit the water, when the spacecraft hit the water. We waited until the crew stepped out on the deck of the carrier. And we figured that was terra firma enough that we could say they're not going to drown, the spacecraft's not going to sink, because we always felt that they weren't safe until they got on that carrier deck. And that's the moment they stepped on the deck. You can see Gene Kranz there. In fact, that is the 4 flight directors that worked Apollo 13. My team was to do the landing on that mission. Of course, that didn't happen, so my team ended up just in the cycle to get them home. Here we are at 14. Notice the hairdo now. On me, the age of Aquarius was growing on us. And it was happening in the control center, although very modest. But that's Glenn Lunny, flight director, sitting. That's Gene Kranz I'm talking to, and it looks like I'm disagreeing with him on something. I don't know what it was. But here I am at 15. Now the age of Aquarius is really upon us. And then one final one, and this is Apollo 17, last mission. I don't have a good picture of this. I got a team picture, but it's so far back. If you saw my face, I had a Fu Manchu. So this was the ultimate, age of Aquarius adaptation. When we were young, we were all young. It was an era of we. We almost lost the pronoun I. We always said we, even whether we did it or whether the astronauts did it. We got them, or we went into the lunar module and we weren't even there. And the crew did the same thing. It was such a strong team feeling with everybody pulling together. The word I just didn't show up much. And we had a great leadership. And the reason I say that is for a number of reasons. One is they pushed decisions down to the lowest level, not elevate them to the highest. It didn't make any difference whether you were a GS7 or a GS16. Made no difference. If you were in charge, you were in charge. That leadership started at the top. During Apollo, we had 3 presidents, in both 2 of them in one party and one in the other. Their support never wavered. Say the same thing with Congress. Congress supported us. But it was it was a different time. It was in the Soviet Union, we were in a Cold War. I can tell you, we never in mission control thought about what the Russians were doing, or the Soviet Union at that time. We didn't have time. It was kind of like when you play a ball game, play your game, don't try to figure out what they're doing. Just play your best and you'll better chance of winning. I'm going to give you a personal leadership story that I want to leave with you. This is an artist's conception of the command and service module. This was the mothership. The command module in the front, the heat shield, the only thing that would get them back in is right here. But all of this is full of propulsion, electrical. It's where the fuel cells were that produced electricity, batteries, environmental control. All of that was in the back. And we jettisoned that before we went back into the atmosphere, very near back to Earth. I drew this, or I had this drawing instead of a picture because I wanted you to see how clean the command module and service module were. It's a very clean vehicle. And here is Apollo 13, taken from the command module after they separated the service module. And all of this area here is what was blown out. It blew that whole panel off and could have really been fatal. It could have been it could have been, I call it curtains. It would have been curtains. But it was isolated enough that all we did is that we ended up losing and we weren't sure the service propulsion system. We never fired it again because we didn't know what it had done to the lines, fuel lines back there. So I want to back up just a second. The leadership part of this that was so important is that When the explosion happened and we were headed toward the moon, we were about 200,000 miles from Earth, still headed toward the moon, and thank goodness we had the lunar module still with us. That became our lifeboat and got us home eventually. But we had a decision to make. Do we do a direct return where you would just turn the vehicle and burn everything you had and get back to Earth as fast as you can? Another was just a slingshot around the moon using its gravity force to do that. But that was going to bring us down where we had no recovery forces. We could hit the water, but we wouldn't have any recovery. And the third option was to go around the moon. And we ended up calling this a PC+2 option, parasynthian, which is the point of closest approach as you go around the moon, plus 2 hours. We could do a maneuver to speed up the return and also get them back where we could get a carrier underneath them. So it came time, Glenn Lunny and I, our two teams had worked that problem. We had those three options, and we decided the best thing we could do, we better brief the management. We didn't normally have to do that kind of thing, but this was so far off that we figured we'd better. So we went to a private room, and I was, I think, 34 then, he was 32. And we were looking into the eyes of NASA's leadership. The NASA administrator, the head of the whole agency, was there. Our center director, Von Braun, was there. Debus, who was one of Von Braun's people, who was actually director at Kennedy Space Center, was there. Deke Slayton, the head of the whole astronaut business. And Chris Kraft and Bob Gilruth, the director of the Johnson. It was like looking into the eyes of the really big boys. So we briefed them on the options. I briefed them on the consumables that each one of those things did. Glenn briefed them on the flight dynamic piece of it. And at the end, we said, our preference is the PC+2 burn. And go around the moon, speed them up, get them home, get a carrier under. Then there was an awkward silence, very awkward. And I figured, uh-oh, here it comes. Have you thought of this? Have you thought of that? Why didn't you think of an option like this? And this delay kept getting longer. I thought we were just going to have to leave. And Tom Paine, the head of the agency, said, what can we do to help you men? And still sends chills. They trusted us. And we said, sir, we have it. We think we can implement it. My team was on duty. I never forget. I walked back in, picked up my headset and said, guys, we got a plan. Let's go. And so we got on it. But anyway, great leadership, did not try to do or pull the job away from people below them that they knew a lot more about things than they did. I see that happen all the time now in corporations, any organization. As it ages, tends to pull the decision making up till you finally get it to a point where it's being made by somebody that don't know what they're talking about. So I'm going to go through this pretty fast. We were kind of hanging on after Apollo. We flew Skylab and ASTP, the Apollo-Soyuz project. This was spare hardware. Fred mentioned that they canceled 18 and 19. They had already canceled 20. But this was spare hardware that was left. And it served a good bridge. That was actually our first space station, Skylab. That was a empty S2 stage of a Saturn V that became the lab. Apollo-Soyuz was primarily political. That's when we were trying to be a little more friendly. And we docked with Apollo, with the Russians, and Tom Stafford was the commander of our side. And Leonov was the commander of the Russian side. He had done the first EVA ever. They beat us on that too. And one of the funny things I learned, I got to know Leonov pretty well, and he said, it's really funny to hear Tom Stafford try to talk Russian with an Oklahoma accent. And so it was a good mission, but we could have probably done it. Then we got to the shuttle. Most of you guys lived through a lot of the shuttle era. Started in 81, went to 2011, 30 years. And I'm going to go through this fast because I want to leave time for questions. They launched the Hubble, went up and got the Hubble and pulled it into the cargo bay and fixed the lens on it that had been ground incorrectly. They put a contact lens on it, if you will, and went back again later to replace the electronics in Hubble. That's one reason it's still working so well. They took up shuttle took up most of the parts, big parts. The Russians did some, but for the most part, we built that with the shuttle. And then on July 21st of 2011, the 135th mission shuttle landed, and that was the last time it flew. I'm not going to go into Challenger and Columbia because those deserve more time than I have. But when we landed the shuttle, the only way we could get to the ISS, the International Space Station, we had to buy seats on a Russian Soyuz. And that's why we got crew up and down until 2020. And SpaceX got to they launched called Demo 2. Demo 1 was unmanned. Demo 2 had 2 guys in it, 2 NASA astronauts. They went to the station and docked up on May 31st, and on August 2nd, they landed and everything was fine. Since then, we've had several trips by this, and we're going to have more. The first goal, of course, next is Artemis. We've talked about that. Still 240,000 on average. But then we're going to Mars, a Moon-Mars strategy. You're going to start hearing more about that. That's a long way away. It can be as close as 34 million miles. I think I read, you astronomers would know, I think that only happens every 60,000 years or something. Very, very rare. It's about 140 million miles right now. So we got Apollo, we got Artemis. What's the difference? I found this yesterday online on a website called astronomy.com. And I truncated it, but I gave them credit. They said Apollo was setting foot on another celestial body object, and while Artemis is living and working on another world. I think that is very profound. I think it exactly explains what the difference between Apollo and in Apollo, we flew a bunch of sorties out to the moon. We're going to have sustainability with Artemis, where we stay at the moon, learn how to live and work on it. We've got to do it there at this close neighbor before we ever think about going to Mars. That would be too far to try to work out how you're going to do that exactly. Of course, it has the rocket, the space rocket. Orion is the spacecraft that carries the people. You've got a lunar gateway. Just think of that as a space station in lunar orbit. And that's so that people can come from Earth and park. They don't have to go down to the moon right away. The lander is docked, it goes down, comes back to the gateway. You can sustain life here and there until you get a habitat where you can live. So it makes sense. I think it's going to be good. In the meantime, commercial activities, as you all know, have taken off like crazy. These were existing launch vehicles, some of them being phased out by United Launch Alliance. And then we've got Northrop Grumman came in with the SpaceX came in with just the Falcon series. Northrop Grumman came in with the Antares, and Blue Origin, the new Glenn, which hasn't launched yet. The really new commercial launch vehicles, one is by ULA, United Launch Alliance, that's a combination of companies, is the Vulcan. And the one on the right, the Super Heavy by SpaceX, is the one that should launch. They're going to try to launch it tomorrow for the first time. And that's got the lunar lander. That black part on the top is the lunar lander called Starship that would be used if this is successful. That whole thing lands on the moon. But it's the largest rocket thrust-wise ever, including the Saturn V, including the SLS. And Elon's going to try to do that down in Texas tomorrow. Spacecraft have come from several companies. Boeing really had problems with the Starliner, but they're going to get there. Everything else on it, and the Dreamliner is about to fly its first mission. So here's the near future, I think. I think human spaceflight to Earth orbit, down low, is going to become the domain of the commercial industries, commercial space industry. They're already dominating it. SpaceX is launching payloads for the Department of Defense at a very rapid rate. Human spaceflight, then, I think will be left to governments. There's not a business case yet. There may be later. There's just not a business case for trying to go to the moon. And I know there's mining companies that have talked about it, and that might happen, but that's a long way away. I think right now that NASA is doing what it should do. It ought to be thinking deep exploration and not grinding in Earth orbit. So wrapping it up, I'll put all three of those. I'm not going to go through all that, but we've had this past that started really with World War II, I think, ended up in the present where we've actually flown Artemis 1 now. That's already happened. And we've got these other things coming online. Then in the future, we're going to have even more capability. So that's the end. And I appreciate your attention and hope I made some sense for you without getting too technical. And okay. Any questions? Yeah. Yeah, you.
I know it sounds silly, but did NASA just advertise we need a flight director and with a job description, or how did you get into that?
It changed. When I was a flight controller here in Germany. I was guidance, navigation, and systems guy, analyst in mission control. And I reported to the flight director. Well, in those days, Chris Kraft, who was the first flight director on Mercury and was a flight director on Gemini for a while, and then he was elevated to be the head of flight operation. Chris, when he wanted to pick a flight director, he just reached down and said, "You're going to be a flight director." I said, "Really?" And by the way, best job I ever had. That's why I'm wearing this jacket. It says Mission Control, Mission Ops. Best job I ever had. I was 33 years old. I could move a carrier from one ocean to another, and it was crazy. What Glenn Lunny, a colleague, said, going to the moon, he said it was like your parents giving you the key to the car and saying, "You guys take that thing to the moon and back." And he said we were a bunch of kids. It was the best job I ever had. But after Challenger, the selection process for flight directors got harder. In fact, they now go through a certification process. They're named kind of as a candidate, kind of like astronauts brought in as candidates now. And then they have to go through a certain amount of certification simulation experience and get the nod from everybody. I think maybe the way Chris did it was good. It was interesting. Of the 6 of us that did Apollo, 4 of us had military flying experience. 2 did not, but they've been with NASA since they got out of college, and they've been in the early space business. I think that discipline of, it's kind of like Fredo was talking about, that discipline of the military helped in the early days. We had a lot of military guys with us, by the way. We had guys sitting beside us that wearing the same badge we were, and because they had been in the space business longer than we had. And the Army Corps of Engineers built the Cape. They also modified it for the shuttle. Built that 15,000-foot runway that's 300 feet wide and 12 feet thick. So we depended on the military, particularly early on. Not so much now, but getting that flight director nod was up to Chris when in the Apollo era, as long as he was head of flight ops. But as soon as he left, and shortly thereafter, we had the Challenger accident, and I was center director. I had left about a month before the Challenger accident. It changed it completely. By the way, there are fewer flight directors, former flight directors, by far than there are astronauts or former astronauts. So my point is, it's a pretty elite group. I think in the old days, to be honest with you, we had more, for want of another word, power. I think we had a little more power. We could do things on our own. We were trusted. Everybody thought we were geniuses, and we weren't. But you know, kind of let them think it anyway. Another question. Okay, I can hardly see. Is there a hand? Yeah, right there. No, and I'll tell you, the Hidden Figures was a good exposure of the 1960s and 70s. Factually, it was not complete in my judgment. There were other pods of analysts that were women. They were white women that did the same job. They worked mostly. I never met one of them. They never were in Houston, and that's where I was. But in Mercury, they did the lion's share of the work. Those early flights, John Glenn knew several of them. And in fact, I can't verify this because I wasn't around for his launch, but he said right before he got on board, Mercury said, or before they were making the go, no-go decision whether they were going to try to launch, he asked if one of those ladies at Langley had checked the numbers. And they said yes. But they never calculated anything for us in Houston because by that time, we were doing our own. And we had, boy, this was really fancy. We had 5 IBM 360s. They, 3 of them had filled this room. We had a whole floor on the bottom floor of the control center for those 5 computers. We had one online, one on immediate standby, and the others were running calculations for the next flight and everything else. And my point in all that is that the capabilities were changing real fast. Now, the Hidden Figures women did a good job of Earth orbit, early Earth orbit analysis and trajectory planning and that kind of thing. And they did a lot of it on Frieden calculators and things like that, things that were kind of auto-mechanical. They didn't have sophisticated computers then. So I don't take anything away from it. It just didn't tell the whole quite all the story. I wish, but of course that's not what they were trying to do with the movie. And having done 5 movies, been involved in 5 movies myself now, you got to give the director and the producers the opportunity to tell the story they want to tell. But it was factually complete and I think pretty accurate, but it didn't tell all of it. Let me say it that way. Yeah.
Hi, thanks for the talk. How much interaction did you, as a flight director, have with the astronauts before a mission?
Tons. In fact, I was a lead flight director, which a lead flight director was a pre-mission responsibility. I was on 12, 15, and 17. I was lead flight director. Lead flight director had to make sure that all the flight plan was in order, the mission rules, the emergency procedures, all of that. And so you had to work all of that with the crew. So I lived with the Apollo 12 crew because that was that was the first one I did. I got a little better at it on 15 and 17. But we all lived together. Our kids went to school together. Our wives they knew each other. Now we were spread out in some cases in different housing development, but most of them were with us. We lived in a place called Nassau Bay, which is right outside the front gate, across a 4-lane highway now, 6-lane highway now. It's a dirt road. That's why I think we had that we era where, I can remember telling newsmen, well, we got over into the lunar, that's why I remember, 13 had to be, got over into the lunar module and did something. And it was like I'd done it, and, but nobody ever noticed it. And they were all fun people, some of them funnier than heck. Pete Conrad on Apollo 12, he was the commander, one of the funniest guys I've ever met in my life. And he's the one that, when he got off the steps on the moon, that may have been a small step for Neil, but it was a hell of a big one for me, because he was about my height. And he said, that was a hell of a big one for me. And so he was like that. That's why his brain worked. And then you had very serious people like Ed Mitchell, who on 14, he was a lunar module pilot on 14. Ed was quiet, reserved, science-oriented guy. Great guy, though, really fun. He was fun. When you got him, give him a beer, and he loosened him up a little. We've got time for 1 or 2 more max. Okay, right there. Are you standing up? Who is it? Okay, again. Could you speak up just a little bit? I'm having a hard time hearing you. Yeah. Well, what space does at the end of the day, I think, and the question is oriented toward photography and in space and astrophotography and so forth. For one thing, it gives you a unique view of everything, both down and up. But the second thing is the clarity with no atmosphere, that everything they did, it was like that Earthrise. I mean, it looked like it was chiseled. It was so crisp. And of course, now we got the Webb painting galaxies that we never thought about. And it's doing something entirely different, of course, with infrared. But I think the whole thing is in a change arena where we're going to see things that we haven't seen forever, and we already have with Webb. And then the Hubble is still doing good work. But in terms of, I'm probably a little out of my league to answer your question, but my opinion is that I think it's only going to all get better quickly, I should say. Come a little closer. Can you repeat that?
If Artemis goes successfully, when do you think we'll get to Mars?
Well, it's a really good question. Should have been standing over here. Now I can see all of you. That's a good question because, Mars is only available every once in a while. When it's on the far side of the sun and we're over here, we're not in the same orbit. So this thing keeps changing. And it's generally, I think the next close option, and that's in a 140 million mile class, I think, is 2030. I don't think we'll make Mars in 2030. I think it would be the opportunity, maybe the next one, which would be when you're going to be really interested in whether they can do it or not. I think would come in the 2040, 2050 range, somewhere in there. And that's when it's close enough that it doesn't, if Mars was on the far side of the sun and you're way over here on the other side, that makes the trip even longer to get there. And it's already 6-8 months with the propulsion that we have now. Yeah. And listen, we're out of time. We don't want to hold up the raffle. I've been told that that's an important milestone. So thank you for your attention and really appreciate it.
Thank you very much, Jerry. Thank you very much. Thank you. Great job.
My pleasure.
Great job. Good job.
Yeah.
Good job. Thank you. Okay.
Thank you.